Hello there and welcome to Science for Sleep, where curiosity gets comfortable, the lights of the universe are turned down just a little, and even the most energetic events in space are allowed to explain themselves without shouting. Tonight, we're going to look at a kind of stellar outburst that seems to have borrowed part of its name from several different corners of astronomy. It is called a red nova, or more precisely a luminous red nova, and it can appear when two stars that have spent years, centuries, or far longer circling one another finally lose the space between them and become one. This is not a quiet adjustment. Stars are not known for moving house neatly. Gas is thrown outward, the system brightens, its colour changes, and for a while, a point of light that may once have seemed completely ordinary becomes one of the most interesting objects in its part of the sky. Before we move any closer, where are you listening from tonight? And what does the sky look like where you are? Perhaps you can see a few stars through a window. Perhaps the clouds have arranged another evening of keeping the entire universe to themselves. Or maybe you are listening in daylight, which is perfectly acceptable. The stars are still there. They are simply being outperformed by one nearby star that has no understanding of indoor lighting levels. And what time is it for you right now? There is something fitting about asking that while we prepare to follow two stars through an event that may unfold slowly for years, then suddenly brighten across days or weeks, before settling into a long and complicated aftermath. If you find these gentle journeys through science soothing, interesting, or useful, for giving your thoughts somewhere quiet to wander, you can leave a like and subscribe. It helps this calm corner of the internet reach other people who may also enjoy learning about stars while attempting the ambitious nightly project of falling asleep. There is no need to remember every term. No examination is waiting at the end. You can simply settle in, let the details pass at their own pace, and follow the general shape of the story. Imagine then that we're looking across the Milky Way at a distant pair of stars. From Earth, even through a powerful telescope, they may appear as a single point. The distance between them could be millions of kilometers, yet from our position, they are blended together by the enormous space between their system and ours. They orbit a shared center of mass, each star responding to the gravity of the other. One may be larger, one may be hotter, one may have already used much of the hydrogen in its core and begun to swell. Their arrangement may have remained stable for a very long time, but stable does not always mean permanent. As one star grows, its outer layers can move closer to its companion. Gas may begin to flow from one star to the other. The orbit can change. Angular momentum can be carried away. Material may surround both stars. What began as two separate objects following predictable paths can become a system in which each orbit brings them closer. Each exchange of matter changes the balance, and each change makes the next orbit slightly different. It is a difficult process to picture, because stars are so large and the timescales are so unfamiliar. Yet the basic problem is almost domestic. Two very large occupants are trying to share an increasingly small amount of room, and neither of them has agreed to move the furniture. Eventually, under the right conditions, the pair may enter what astronomers call a common envelope. The outer atmosphere of one star expands around both stellar cores, so the two stars are now moving inside the same enormous cloud of gas. As they travel through it, friction and gravitational interactions remove energy from their orbit. The distance between them shrinks, gas can be pushed outward, the system becomes unstable. Whether the envelope is successfully expelled or the two stars continue inward until they merge depends on the masses, the structure of the stars, the speed of the interaction, and details that astronomers are still working hard to understand. A red nova gives us a rare view of this hidden part of stellar life. Most of the time, the important action in a close binary system is difficult to observe directly. The stars are distant. The gas around them can obscure what is happening. The decisive phase may be brief compared with the millions or billions of years that came before it. Then the system brightens, and suddenly telescopes across Earth have a reason to turn toward it. Light that has travelled through the galaxy arrives carrying information about temperature, speed, chemical composition, dust, and the motion of ejected material. A stellar relationship that may have been changing unnoticed for years becomes visible because it has reached the point where subtlety is no longer an option. The name can be confusing. A red nova is not simply any nova that happens to look red. Astronomy has a long tradition of using familiar words for new discoveries and then spending decades explaining why the names do not quite mean what people reasonably assume they mean. A classical nova usually involves a white dwarf pulling material from a companion star. Hydrogen builds up on the white dwarf's surface until a thermonuclear runaway produces a powerful eruption. The white dwarf itself survives and may repeat the process. A supernova is much more violent and often marks the destruction of a star or the thermonuclear disruption of a white dwarf. A luminous red nova belongs to a different story. In the leading interpretation, it is connected to a merger or a common envelope event involving ordinary, non-compact stars. Instead of one star exploding because its core has collapsed, or a white dwarf igniting stolen gas, two stars are losing their separate identities. That does not make the event gentle. The orbital energy of two stars is enormous. As they spiral together, some of that energy can be transferred into surrounding gas. Material is heated, accelerated, and expelled. The system may brighten dramatically, yet compared with a supernova, the expansion speeds are often slower, the temperatures can evolve toward cooler values, and the surviving remnant is not necessarily a neutron star, a black hole, or a dispersing cloud with no central star left behind. There may instead be a single swollen object, still hidden within dust and gas, trying to settle after one of the largest rearrangements a stellar system can experience. The word red describes an important part of what observers see. These events often become cooler and redder as they develop. Early light can be brighter at shorter wavelengths, but as the expelled material expands, its surface cools. Molecules and dust can form. More of the energy emerges at red and infrared wavelengths. To human eyes, if the event were close and bright enough to see clearly, it could take on a warm reddish appearance. Of course, standing close enough for a better view would be an extremely poor observing strategy. Space offers many impressive sights, but it remains strangely resistant to the idea of a safe front row seat. The colour change is not merely decorative. It tells astronomers that the physical conditions around the merger are changing. A hot, compact source can produce bluer light. A large, cooler photosphere produces redder light. Expanding gas can absorb and reprocess radiation. Dust can hide visible light while glowing in the infrared. Spectra can reveal hydrogen, metals and molecules forming in material that was recently part of one or both stars. Each shift in brightness and colour adds another clue, rather like watching the lights change in a room and trying to work out what someone is doing behind a closed door. There's also no single standard red nova that behaves exactly like every other. Some events are modest by cosmic standards and occur in relatively low-mass binary systems. Others are far brighter and may involve more massive stars. Their light curves can show more than one peak. Some rise quickly. Some remain bright for longer. Some create large amounts of dust. The term covers a family of related events, rather than one perfectly uniform explosion. This is part of what makes them useful. Differences between them may reveal how the masses of the stars, their evolutionary stages, and the geometry of the merger affect the outcome. For a long time, astronomers saw unusual red outbursts without knowing exactly how to classify them. An object would brighten, cool, form molecules, and refuse to behave like the familiar kinds of novae or supernovae. That is an awkward moment in science, but also a productive one. Nature is under no obligation to fit into the folders already prepared for it. When observations do not match the available categories, researchers can either complain about the filing system or learn something new. Usually after a suitable period of complaining, they choose the second option. One of the most famous objects associated with this class is V838 Monocerotis. In 2002, it produced an extraordinary outburst and later became surrounded in Hubble images by what looked like expanding shells of illuminated material. The display was a light echo. The original flash travelled outward and lit up dust at increasing distances from the star, allowing us to see different parts of the surrounding material as the light reached them. The dust itself was not racing outward faster than light. It was more like a dark room being revealed section by section as a moving beam passed across it. The images were so unusual that they became some of the best-known pictures of a stellar outburst, even though the event itself was difficult to explain. V838. Monocerotis will deserve a closer look later because its behaviour helped force astronomers to take this strange class of objects seriously. For now, it is enough to imagine the surprise. A star brightens unexpectedly. It does not behave like a normal nova. It grows very cool. Its outer layers expand to an enormous size. Then the surrounding dust seems to bloom in space, as delayed light reveals structures that had been invisible before. It is the sort of observation that makes even experienced researchers pause, recheck the data, and quietly hope that no one asks for a simple explanation before breakfast. Another important object, V1309 Scorpii, gave astronomers something especially valuable: observations from before the outburst. Archival data showed that the source had been a contact binary, a pair of stars orbiting so close together that their outer layers touched. Its orbital period decreased in the years leading up to the 2008 eruption. The stars were spiraling closer, and the system's changing rhythm was recorded before they merged. This was a major clue connecting luminous red novae with stellar mergers. Instead of seeing only the bright aftermath and trying to reconstruct what had happened, astronomers had found evidence of the approach. Think about how unusual that is. In most dramatic astronomical events, we arrive late. We see the explosion, the flash, the debris, or the remnant. The earlier stages may have happened before telescopes existed, before humans existed, or before anyone happened to look in the correct direction. With V1309 Scorpion, routine observations quietly recorded a binary system moving toward disaster. The data did not arrive with a label saying, "Please keep this, it will become important." It sat among countless measurements until researchers looked back and recognized the pattern. Astronomy often advances in this way. The universe performs something remarkable, and the evidence waits patiently in an archive until someone asks the right question. This also raises a slightly unsettling possibility. Somewhere in the sky tonight, another close binary may be approaching a merger. It may look unremarkable. Its brightness may fluctuate in ways that seem minor. Its orbit may be shrinking by a small amount. Telescopes may already be gathering the evidence without anyone yet realizing how the story will end. Predicting exactly when such a system will merge is extremely difficult. Stars are not mechanical clocks with exposed gears. Their interiors move, their outer layers respond to heat and gravity. Gas flows through complicated paths, and magnetic activity can alter what observers see. A prediction that appears precise can be undermined by physics hidden beneath the surface. Still, the hope of finding a red nova before it erupts is irresistible. If astronomers can monitor a system throughout the final approach, they can watch how mass loss begins, how the orbit changes, how quickly the stars spiral inward, and how the bright transient develops. They may learn whether material is expelled in stages, whether jets help remove the envelope, and how dust forms after the merger. Each observation would help with a problem that reaches far beyond red novae themselves: the common envelope phase. Common envelope evolution is one of the most important and least certain processes in the study of binary stars. It can determine whether two stars merge, remain as a tighter pair, or later produce systems containing white dwarfs, neutron stars, or black holes. Some compact binaries that eventually emit gravitational waves may have passed through a common envelope earlier in their history. Yet the process is difficult to simulate, and difficult to observe because it happens quickly, involves enormous differences in scale, and depends on gas dynamics, radiation, gravity, and stellar structure all at once. A red nova may be one of the few times the universe places a bright marker over the scene and says, in effect, the difficult part is happening here. Even so, we should be careful not to imagine that every detail is settled. The broad connection between many luminous red novae and stellar mergers is strong, but individual events can be complicated. Some may involve incomplete mergers. Some may be dominated by the ejection of a common envelope. Massive stars can produce eruptions that resemble merger events. Observers classify distant transients using limited data, and two objects that look similar in visible light may have different histories. Science becomes reliable not by pretending uncertainty has vanished, but by narrowing the possibilities as evidence improves. That uncertainty is part of the reason the simple question, what is a red nova, really is worth asking. At first, the answer seems easy. It is the outburst produced when two stars merge. But each word opens another question. What kinds of stars? How close were they? What started the unstable transfer of mass? Did both stars survive until the final collision? How much material was expelled? What powered the first peak of light? Why did the system grow redder? What formed inside the cooling gas? What remained at the centre after the visible display faded? And how can an event that occurs thousands or millions of light years away reveal the movement of matter between two stars we cannot resolve separately? To answer those questions, we will have to slow the event down. We will begin before the brightening, while two stars still orbit one another. We will watch the larger star expand and see how gravity guides gas toward its companion. We will enter the shared envelope where orbital motion is converted into heat and movement within the surrounding material. We will follow the final inward spiral and the release of energy. Then we will remain after the brightest light has passed. When the gas cools, molecules appear, dust gathers, and the merged remnant begins a new and uncertain stage of its life. For now, picture that distant point of light once more. It appears small because everything in astronomy appears small when it is far enough away. Yet within that point are two enormous spheres of plasma, each with its own internal layers, rotation, magnetic fields, and history. They may have formed from the same cloud and spent their entire lives together. They have exchanged light, gravity, and perhaps material. One has changed faster than the other. Their orbit has tightened. The larger star's atmosphere has spread outward until the old boundary between them has become difficult to define. No sound reaches us from the system. Space between the stars and Earth is far too empty to carry it. What arrives instead is light, delayed by distance, and altered by everything that happened before it escaped. The brightening may tell us that gas was launched outward. The red colour may tell us that the radiating surface expanded and cooled. Infrared observations may reveal dust. Spectral lines may show matter moving toward or away from us. A changing orbital signal, if we were fortunate enough to record it beforehand, may reveal the final tightening spiral. Piece by piece, an event we cannot visit becomes understandable, and there is something unexpectedly familiar in the basic idea. A red nova is not mainly about a star ending because it ran out of fuel. It's about two stars changing each other so completely that neither can continue in its previous form. Their individual histories meet. Their orbital motion becomes heat, expanding gas, and light. What once existed as a pair becomes a remnant with a new structure and a great deal of unfinished settling to do. The result may remain swollen for years, surrounded by material that continues to cool and rearrange itself long after the initial outburst has faded from ordinary telescopes. So, as you rest and let the night continue around you, keep that image nearby. Two stars circle in the dark, not rapidly by human standards, but with a growing sense of inevitability written into their orbit. Gas begins to pass between them. Their shared environment thickens. Energy moves from the orbit into the surrounding envelope. The system is approaching a point from which it cannot return to the tidy arrangement it once had. A red nova sits in an awkward place in the astronomical family tree. Its name sounds familiar enough, but familiarity is exactly what causes the trouble. Hear the word nova, and you might picture a star suddenly flaring into brilliance. Add the word red, and it seems reasonable to assume that this is simply a cooler or more colourful version of the same event. Yet the resemblance is mostly in the temporary brightening. Beneath the light, the mechanism is different. The stars involved are different, and the final result can be different as well. A red nova is not an ordinary nova wearing a warmer coat, and it is not a small supernova that stopped halfway through the performance. It belongs to a separate class of transient events, one that astronomers had to recognise slowly, because the universe did not provide a convenient label when the first examples appeared. The word transient is useful here. In astronomy, a transient is something in the sky that changes noticeably over a limited period. It may brighten, fade, appear where nothing had been visible before, or alter its colour and spectrum. Some transients last seconds, others remain active for months or years. They include stellar flares, novae, supernovae, tidal disruption events, gamma-ray bursts, and several other phenomena whose names can make an observing schedule look like a list of unusually dramatic weather conditions. A luminous red nova is one member of this broad population. It appears, grows brighter, changes, and then fades. But the physical reason for that display is not the same as the better-known explosion surrounding it in astronomy textbooks. To understand the difference, let us begin with an ordinary nova. A classical nova usually occurs in a binary system containing a white dwarf and a companion star. A white dwarf is the dense remnant left after a star similar to the Sun has finished its main nuclear life and shed its outer layers. It contains roughly the mass of a star compressed into an object about the size of Earth. If that white dwarf has a nearby companion, its gravity may pull hydrogen-rich gas away from the companion and collect it on its own surface. The gas becomes compressed and heated as more material arrives. Eventually, conditions at the base of this accumulated layer can become extreme enough for nuclear fusion to begin rapidly. The result is a thermonuclear runaway across the surface of the white dwarf. The newly gathered material burns explosively, and the system brightens by a remarkable amount. Gas is expelled into space at high speed. For a while, a star that may have been too faint to see without a telescope can become visible to modest instruments or, in rare historical cases, to the unaided eye. Then the eruption fades. The important detail is that the white dwarf usually remains. It has not been completely destroyed. If it continues pulling material from its companion, another eruption may occur later. Some systems are known as recurrent novae because they repeat on humanly observable timescales. The white dwarf is rather like an appliance that keeps developing the same alarming fault, except the fault involves nuclear fusion, and no one is willing to approach it with a screwdriver. A red nova does not usually involve this arrangement. There is no requirement for a white dwarf to collect a thin explosive layer on its surface. The light is not primarily produced by a thermonuclear runaway in newly accreted hydrogen. Instead, the energy comes from the interaction and possible merger of two non-compact stars, meaning stars that still possess extended gaseous interiors rather than existing as extremely dense remnants. Their orbital energy, gravitational energy, shocks, expanding gas, and the release of heat from recombining material can all contribute to what we see. The entire structure of the binary may be rearranged. Rather than one star briefly igniting material stolen from another, the two stars may become enclosed in the same atmosphere and then combine. That difference changes the appearance of the event. Classical novae often become hot and blue near their brightest phases, and their ejecta can race outward at speeds of hundreds or thousands of kilometers per second. Their spectra show features produced by rapidly moving gas. A luminous red nova can also begin with a relatively hot early peak, but it typically evolves toward a cooler state. Its later light may be dominated by a large expanding photosphere with a temperature more like that of a cool star. The outflow speeds are often lower than those in classical novae, and far lower than the fastest supernova ejecta. Molecules may appear in the spectrum. Dust may form. The object becomes redder, and much of its energy eventually shifts into the infrared, where human eyes cannot see it but suitable telescopes can. Even the shape of the brightening can provide a clue. Many luminous red novae show more than one broad peak, or a peak followed by a plateau-like stage. The first rise may be faster and bluer. A later, longer phase may be cooler and redder. Different events do not follow one identical pattern, but the repeated appearance of these features suggests that more than one physical process can contribute. An initial ejection may release hot material. Later, faster gas may collide with slower gas expelled earlier, converting motion into heat. As the ejecta expand and cool, ionized hydrogen can recombine, releasing stored energy and helping to support a broad luminous phase. The growing photosphere can reach an enormous size even as its temperature falls. It is possible for an object to become visually impressive, not because every part is becoming hotter, but because a very large amount of cooler material is radiating across a wider surface. Now consider the opposite comparison. If a red nova is not an ordinary nova, could it be a type of supernova? Again, the brightness may tempt us in that direction. Some red novae are far more luminous than classical novae. Observed in another galaxy, they can briefly resemble weak supernovae, especially when the first available data are incomplete. Yet a true supernova generally involves a much more energetic and destructive event. In a core collapse supernova, a massive star develops a core that can no longer generate enough outward support through ordinary fusion. The core collapses under gravity, a neutron star or black hole may form, and a powerful explosion expels much of the star's outer material. In a Type 1a supernova, a white dwarf undergoes a runaway thermonuclear disruption that can destroy the white dwarf. These are not surface flashes or temporary swellings. They are profound transformations involving stellar cores and energies that can make one star rival the light of a galaxy. A luminous red nova is usually less energetic and less luminous than a supernova. It may occupy what astronomers call the luminosity gap between classical novae and supernovae, although nature does not draw perfectly straight borders. Its ejecta generally move more slowly. Its spectrum becomes much cooler. The central object may survive as a merged star rather than collapsing into a compact remnant or being completely disrupted. This survival matters. After a supernova, you may be left with an expanding remnant and, depending on the event, a neutron star, a black hole, or no original white dwarf at all. After a red nova, you may still have a large, unstable, rapidly rotating star hidden behind dust, carrying the combined mass and angular momentum of the former binary. The word explosion therefore needs some care. It is not wrong to say that a red nova produces an explosive outburst. Gas can be expelled violently, the brightness can increase quickly, and shocks can move through surrounding material. But the event is not necessarily an explosion that begins deep in a stellar core. Much of the available energy was already present in the orbit. Two stars moving around one another possess orbital energy, just as any pair of gravitating objects does. When their orbit shrinks, energy must go somewhere. Some can heat and accelerate gas, some can help lift the envelope away from the system, some can be radiated as light. Gravity is not creating energy from nowhere. It is allowing energy stored in the arrangement and motion of the system to be converted into other forms. You can picture this without imagining the stars as hard spheres colliding like billiard balls. A star has no solid surface in the ordinary sense. Its visible edge is a layer of gas from which light can escape, while its density increases gradually inward. When two stars begin to merge, their outer atmospheres can interact long before their denser central regions meet. Gas streams between them. One star may overflow the region where its material remains gravitationally bound most securely to itself. Matter can move through a point between the stars and toward the companion. Some material may form a disk or an extended envelope. Some may leave the system. The merger is therefore less like two stones striking and more like two enormous self-gravitating weather systems, becoming impossible to separate, although even that comparison makes the process sound considerably tidier than it is. Because the interaction develops in stages, the light can also develop in stages. Long before the brightest outburst, a binary may slowly increase in luminosity as unstable mass transfer begins. Material leaving the system can form a thick outflow around the orbit. Collisions within that outflow may release heat. When the final inward motion accelerates, another pulse of mass and energy can be launched. The first gas ejected has had time to travel outward and cool. Faster ejector released later may catch it. A shock then forms where the two flows meet. That shock can provide a fresh source of radiation outside the central stars, sometimes hidden within thick material that absorbs the energy and releases it again at different wavelengths. This helps explain why a red nova cannot be understood by looking only at the instant when the stars join. The system prepares its surroundings. Material lost before the main event creates the environment into which later ejecta travel. The observed brightness is shaped by the history of mass loss, the direction in which gas is expelled, the angle from which we view the system, the opacity of the surrounding matter, and the efficiency with which energy can escape. Two mergers involving similar stellar masses might still produce different light curves if one has already surrounded itself with a dense equatorial outflow, while the other has not. Astronomy is sometimes like trying to understand a meal by examining the steam above the kitchen. You can learn a surprising amount, but it helps to know what happened before the lid was lifted. The cooling red phase provides another important distinction. In a supernova, the ejecta also expand and cool, and some supernovae become redder with time. Colour alone is not enough for classification. Astronomers combine the light curve with spectra, expansion velocities, infrared behaviour, information about the likely progenitor, and observations of the long-term remnant. Luminous red novae often develop spectra resembling those of very cool stars, including strong absorption from molecules such as titanium oxide or vanadium oxide in some cases. These molecules cannot remain intact in extremely hot gas. Their presence shows that portions of the ejecta have cooled dramatically. Dust formation can then hide the central remnant at visible wavelengths and make the system bright in infrared light. A supernova can form dust too, so once again, no single clue works alone. Classification is the result of several lines of evidence agreeing. Was there a massive star at the position before the eruption? Did the source show signs of a close binary? How bright did it become? How quickly did it rise and fade? What temperatures were inferred? How fast were the spectral lines moving? Did the object develop a cool red plateau? Was a surviving star detected later? Did infrared emission continue after the visible light disappeared? Each answer narrows the possibilities. This is why the phrase intermediate luminosity red transient sometimes appears in discussions of these objects. It is a broad observational description for events brighter than typical novae but fainter than ordinary supernova, often with cool red evolution. Yet that category can include more than one physical cause. Some eruptions may come from unstable massive stars rather than mergers. Dust-obscured events can imitate one another. Sparse observations can leave uncertainty. Luminous red nova is generally used when the evidence supports binary interaction, common envelope ejection, or stellar coalescence. But astronomers still debate the interpretation of individual cases. Nature has created several overlapping appearances, apparently because organising our terminology was not among its priorities. There are also similarly named events waiting nearby to cause further confusion. A kilonova, for example, is associated with the merger of compact objects such as two neutron stars, or sometimes a neutron star and a black hole. Its light is powered largely by the radioactive decay of newly formed heavy nuclei in fast-moving ejecta. Despite the shared word nova and the involvement of a merger, a kilonova is not a luminous red nova. The objects involved are different, the material is different, the speeds are different, and the source of the light is different. Some kilonova emission can appear red because heavy elements make the ejecta difficult for blue light to escape, but that redness should not persuade us that the two events belong to the same class. Astronomy's naming system occasionally behaves like a family that has given 6 cousins nearly identical names and expects everyone at dinner to cope. Another neighbouring phenomenon is the outburst of a luminous blue variable, a very massive and unstable star that can eject large amounts of material without immediately undergoing a terminal supernova. Such eruptions can reach impressive luminosities and may be mistaken for unusual supernovae or merger events. The famous 19th century Great Eruption of Eta Carinae is an example of a giant non-terminal eruption. Although its exact mechanism remains an active subject of study, an interaction with a companion may play an important role. These events remind us that brightness alone does not reveal the engine. A star can produce a spectacular display through several very different routes. For observers discovering a new transient, the classification may change as information arrives. On the first night, there may be only a new point of light and a rough brightness measurement. A quick spectrum can show whether hydrogen is present and how broad the lines are. Repeated imaging reveals whether the source is rising, fading, or forming a second peak. Infrared observations show whether the object is cooling or becoming dusty. Archival images may reveal what existed at the location before the eruption. Months or years later, deep observations can test whether a star survived. The final explanation is built gradually, and sometimes the object remains stubbornly between categories even after a considerable amount of telescope time. That patience is especially important because a red nova can hide its central mechanism behind its own ejecta. The visible surface during the outburst may not be the surface of either original star. It can be a photosphere formed within expanding material far outside the central remnant. We see the layer from which photons can finally escape, not necessarily the place where most of the energy was first released. As the material expands and becomes more transparent, our view moves inward through different layers. Spectra, taken at different times, therefore sample changing regions of the outflow. The event is not one fixed picture, but a sequence of temporary surfaces. The energy budget places red novae between familiar categories without making them merely halfway versions of either one. Their radiated energy can be substantial, but radiation may account for only part of the total. A large amount can remain as kinetic energy in moving ejecta, or as heat and rotation in the remnant. The brightest visible stage is only the portion the system manages to send toward us as photons. It is not a complete accounting of everything the interaction has done. A relatively faint event could still involve major structural change if much of its energy goes into expanding or unbinding material, rather than visible light. One reason astronomers are interested in finding red novae in other galaxies is that a larger sample allows them to compare event brightness with the likely masses of the progenitor systems. In general, interactions involving more massive stars can produce more luminous transients, although the relationship contains considerable variation and depends on how efficiently orbital energy becomes radiation. Nearby examples within the Milky Way can be studied in fine detail, but are rare and may be hidden behind interstellar dust. Surveys of other galaxies watch enormous populations of stars at once, increasing the chance of catching bright mergers, even though each source appears as a tiny unresolved point. Modern time domain astronomy is particularly well suited to this search. Telescopes repeatedly image large areas of sky and compare each new exposure with earlier ones. Software flags objects that have changed. Follow-up teams obtain spectra and observations at other wavelengths. A red nova that might once have been noticed only after reaching maximum brightness can now be detected during its rise. Earlier detection gives astronomers a better chance of seeing the hotter first stage, measuring the initial outflow, and connecting the later red emission with what came before. It also allows them to discover how diverse these events really are, instead of selecting only the brightest and longest-lasting examples. There is another practical difficulty. We often discover these outbursts at great distances, so several different physical situations can be compressed into the same small amount of observational information. Imagine seeing only the glow behind a closed curtain. You may know that something brightened, changed colour, and then became hidden by dust, but you cannot immediately tell whether two stars merged completely, whether an envelope was expelled while the central pair survived, or whether an unstable single star produced an eruption that happened to look similar. Numerical models help, but the gas behaves in 3 dimensions. The stars rotate, radiation moves through material of changing density, and the relevant scales range from compact stellar cores to outflows spreading across billions of kilometers. Even the largest computer simulations have to simplify something. This is why researchers often speak carefully about merger candidates, likely common envelope events, and probable luminous red novae. Scientific caution can sound less exciting than a firm declaration, but it is more useful. A good classification should remain open to revision when new evidence appears. V1309 Scorpii provides unusually strong evidence because its shrinking contact binary orbit was observed before the outburst. Other systems are interpreted by comparing their behavior with that clear example. The more pre-eruption binaries astronomers identify, the easier it will become to separate genuine stellar mergers from other cool red transients. The central distinction, however, is simple enough to carry with us. A classical nova is usually a thermonuclear eruption on the surface of a surviving white dwarf. A supernova is a much more energetic terminal or core-transforming catastrophe involving core collapse or the thermonuclear destruction of a white dwarf. A luminous red nova is generally the visible consequence of severe interaction between ordinary stars, often during a common envelope event and merger. It is powered largely by the conversion of orbital and gravitational energy, then shaped by mass ejection, shocks, recombination, expansion, cooling, and dust formation. It may leave behind one merged star where 2 once orbited. Once that distinction is clear, the name becomes a little less misleading. The event is nova-like because it appears as a new bright source in the sky. It is luminous because some examples exceed ordinary novae by a wide margin. It becomes red because the expanding material cools, develops a large radiating surface, forms molecules, and frequently produces dust that shifts much of the observable energy toward longer wavelengths. Each part of the name describes something about the appearance, while the deeper explanation lies in the binary system. Still, the outburst is only the visible part of a much longer process. The sudden light may last for weeks or months, but the relationship between the stars may have been changing for thousands or millions of years. One star evolves and expands. Its companion races tides across its surface. Rotation becomes linked to orbital motion. Gas begins to approach the boundary beyond which it can no longer remain attached to its original star. At first, the transfer may be controlled. The companion receives material, and the orbit adjusts. Under other conditions, the flow becomes unstable. The more mass that moves, the more the star's structures and orbit change, causing still more mass to move. The system does not know that astronomers have divided its behavior into neat categories. From the star's perspective, there is only gravity, pressure, heat, motion, and matter responding to changing conditions. The same pair can pass gradually from an ordinary binary into a mass-transferring binary, then into a contact system, a common envelope, and perhaps a merger. The red nova is the moment when this progression becomes bright enough for distant observers to notice, but it began while the system still looked almost calm. That earlier calm can be deceptive. 2 stars may orbit one another with no obvious collision because each remains inside its own gravitational territory. Yet the shape of that territory depends on their masses and their separation. As one star swells, its outer layers can reach a point where the companion's gravity gains a stronger influence. Gas then begins to flow through the narrow region between them. If the expanding star responds by growing even larger, or if the orbit shrinks as material moves, the flow can accelerate. A stable exchange becomes a runaway interaction. Angular momentum also has to be considered. It is the reason the stars orbit instead of fall in directly together. For the separation to decrease greatly, angular momentum must be transferred elsewhere. Gas leaving the system can carry some away. Tidal forces can move some into the rotation of the stars. Friction inside a shared envelope can take energy and angular momentum from the orbit and place them into surrounding matter. The stars spiral closer not because gravity has suddenly appeared, but because the orbital support that once kept them apart is being redistributed. Long before any deep red glow appears then, the system is already changing in ways that will decide the character of the outburst. The masses of the stars determine how they respond to losing or gaining material. Their evolutionary stages determine how tightly their envelopes are bound. The initial orbital distance determines when contact begins. The direction and amount of mass loss determine how quickly the orbit changes. Even a third star in a wider orbit could disturb the pair over long timescales. By the time telescopes detect the transient, many of the important choices have already been made by the quiet physics of the preceding binary life. Long before the two stars share one atmosphere, they must first lose the balance that once kept them comfortably apart. A binary orbit can look permanent when seen over a human lifetime. Night after night, year after year, the stars continue circling their common centre of mass, and nothing seems especially urgent. Yet a close binary is not a pair of finished objects moving through an empty clockwork. Each star is changing inside. Each one raises tides on the other. Their rotation, mass, size, and separation can all evolve, and a small adjustment in one part of the system can slowly alter everything else. The eventual red nova may brighten in a matter of days or weeks, but the conditions that make it possible can develop over millions or even billions of years. To picture the orbit properly, it helps to stop imagining one star sitting still while the other travels around it. Both stars move. If their masses are equal, they circle a point halfway between them. If one is much heavier, that shared centre lies closer to the heavier star, which makes the smaller companion travel around a wider path. Even the larger star still moves a little. Gravity continually pulls them inward, while their sideways motion prevents a direct fall. The result is an orbit, which is really a continuous fall that keeps missing its destination. This arrangement can remain stable for a very long time, provided the stars keep most of their mass, retain enough angular momentum, and remain small compared with the distance separating them. Angular momentum is central to the whole story. It is a measure of rotational motion, and in a binary system much of it is stored in the orbit. The stars cannot simply decide to move closer while everything else remains unchanged. If the orbit shrinks, angular momentum has to be redistributed or carried away. Some can be transferred into the spins of the stars, some can leave with escaping gas. Magnetic winds may remove a little over long periods. In very compact systems, gravitational radiation can also take energy and angular momentum away, although that effect is usually more important for extremely close compact objects than for the ordinary stars involved in many luminous red novae. The inward spiral is therefore not a single pull of gravity. It is a long negotiation over where the system's motion is allowed to go. At first, the two stars may have formed together from the same collapsing cloud of gas. One could be slightly more massive than the other, which may not sound important until stellar evolution begins. A more massive star uses its nuclear fuel faster. It develops higher pressure and temperature in its core, shines more brightly, and leaves its main sequence sooner. The difference might be modest, but over enough time, it means that one star begins to expand while its companion is still living a quieter life. The older-looking star may become a subgiant or giant, building a dense core while its outer envelope spreads into a much larger volume. A star does not expand because more matter has been added to its surface like air entering a balloon. Its internal structure changes as fuel is exhausted in the core and fusion shifts into surrounding shells. The temperature and pressure profile adjust. The outer layers respond by moving outward, becoming cooler and more diffuse. A star that once fits safely inside its part of the binary can eventually approach the region where the companion's gravity begins to compete strongly for its gas. That invisible gravitational boundary is described using something called a Roche lobe. The Roche lobe is not a physical shell. You could not fly through it and hear a helpful chime. It is a region around each star inside which matter is more strongly associated with that star than with its companion. The two lobes meet near a saddle point in the gravitational field called the inner Lagrange point, or L1. Near that point, material can pass from one star's domain into the other's with relatively little additional energy. As long as both stars remain smaller than their Roche lobes, each can keep its outer layers largely to itself. Once an expanding star fills its lobe, however, gas near the surface can begin to flow through L1 toward the companion. This process is called Roche lobe overflow, and it is one of the most important mechanisms in binary star evolution. The star losing material is usually called the donor, while the star receiving it is called the accretor. Those names sound wonderfully orderly, as though the pair completed the proper forms before exchanging several percent of a star. In reality, the gas follows a complicated path shaped by gravity, pressure, rotation, and the motion of the orbit. It may strike the receiving star directly if the stars are close enough. In other systems, the stream misses the accretor's surface and wraps around it, forming an accretion disk. At the beginning, mass transfer does not always lead to disaster. Some binaries exchange material in a relatively stable way. The donor loses gas at a rate that allows its structure and its Roche lobe to adjust together. The companion accepts at least part of the flow. The orbit changes, but not so rapidly that the stars immediately plunge together. This controlled exchange can continue for thousands or millions of years and can radically alter both stars. The original lighter star may become the more massive one after receiving enough material. Its rotation can speed up. Its surface chemistry may carry material that was once buried inside the donor. Binary evolution is full of stars that look younger, hotter, or stranger than they would have looked if left alone. Whether the transfer remains stable depends on several connected responses. First, how does the donor's radius change when it loses mass? A star with a deep convective envelope may expand when material is removed quickly, which can make the overflow worse. Other stars may shrink and pull back inside their Roche lobes. Second, how does the Roche lobe itself change as the masses and orbit change? If the lobe shrinks faster than the star can shrink, more of the donor lies outside its gravitational boundary, increasing the transfer. Third, how much of the gas stays in the binary, and how much escapes while carrying angular momentum with it? These questions decide whether the interaction settles into a manageable flow or becomes a runaway. The mass ratio matters greatly. Suppose a relatively massive donor transfers material to a much lighter companion. As the donor loses mass and the companion gains it, the orbital response can shrink the separation under certain conditions. The donor then finds its Roche lobe becoming smaller, while its outer layers are already spilling across it. More material escapes, the orbit changes further, and the flow strengthens. If the companion cannot accept the incoming gas quickly enough, the excess matter accumulates around the system rather than joining the star neatly. A transfer stream that began as a narrow bridge can become a thick shared environment. There is a limit to how rapidly an ordinary star can absorb matter without reacting. Incoming gas brings energy and angular momentum. The accretor may swell because it cannot radiate the added heat quickly enough. It can spin faster as the material lands with substantial sideways motion. Once its surface approaches the speed at which centrifugal effects become important, accepting more angular momentum becomes difficult. Some of the gas may then leave the binary through outer Lagrange points, or form an extended envelope. So even though we call one star the receiver, it may resemble someone trying to catch water from a fire hose using a teacup. Tides add another layer to the interaction. each star's gravity slightly distorts the other, pulling it away from a perfect sphere. If the stellar rotation does not match the orbital motion, the tidal bulge is carried out of alignment. Internal friction then converts some organized motion into heat and gradually pushes the system towards synchronization, where each star rotates once during each orbit and keeps roughly the same side facing its companion. The Moon does this with Earth, although a close stellar binary is far more deformable and far less suitable for an evening stroll. Synchronization can temporarily create order, but it also transfers angular momentum between the orbit and the stellar spins. As a star expands, its moment of inertia increases, meaning it requires more angular momentum to keep rotating at the orbital rate. Tidal forces can take that angular momentum from the orbit. The orbit then loses some of the motion supporting its separation and becomes smaller. The stars move closer, the orbital period shortens, and the tidal interaction strengthens. Under certain conditions, the orbit no longer contains enough angular momentum to keep a large stellar envelope synchronized. This can contribute to an instability that drives the companion inward. One such condition is often called Darwin instability. The name does not refer to biological evolution, natural selection, or a particularly troublesome voyage on the Beagle. It describes a situation in which too much of the system's angular momentum is tied up in stellar rotation compared with the orbit. A synchronized state can no longer remain stable. The orbit begins to shrink more rapidly as it tries, and fails to maintain the shared rotation. In merger models for systems such as V1309 Scorpii, this kind of instability may help explain the final acceleration toward coalescence, though real stars can combine several mechanisms rather than politely selecting just one. Magnetic activity can also influence some close binaries over long periods. Cool stars with convective envelopes can support magnetic fields and magnetized winds. Gas escaping in such a wind remains linked to the magnetic field for a time and can carry away more angular momentum than an ordinary unmagnetized outflow. The star's spin slows, tides transfer angular momentum from the orbit back into the spin, and the orbit gradually shrinks. This process, called magnetic braking, can help bring already close stars into contact. It is slow compared with the final merger, but slow processes are often responsible for delivering a system to the edge where a faster instability takes over. Stellar winds can change the orbit in other ways as well. If mass leaves gently from the system without taking an unusually large amount of angular momentum, the orbit may widen because the total gravitational attraction decreases. If the escaping gas is focused through a particular region, or forms a circumbinary structure, it can remove much more angular momentum and encourage shrinkage. There is no universal rule saying that losing mass always moves stars closer, or always moves them farther apart. The result depends on where the gas leaves, how fast it moves, which star lost it, and what fraction the companion captures. Binary evolution is less like following one recipe, and more like discovering that the ingredients have started exchanging themselves, while the oven changes size. As the orbit tightens, each circuit becomes shorter. A pair that once took weeks to complete an orbit might eventually circle in days or hours, depending on the sizes of the stars. Their surfaces can become strongly distorted, stretched toward one another by tides and rotation. Seen from Earth, such a system may vary in brightness with a regular pattern. The stars present different projected areas as they orbit. They may partially eclipse one another. Their heated or distorted surfaces may contribute unequal amounts of light. By measuring these repeated changes, astronomers can estimate the orbital period even when the two stars cannot be seen as separate points. This was crucial for understanding V1309 Scorpii. Before its 2008 outburst, the system had been monitored by the Optical Gravitational Lensing Experiment, usually shortened to OGLE. The survey repeatedly measured the brightness of huge numbers of stars toward dense regions of the Milky Way. V1309, Scorpia's progenitor, showed a repeating pattern with a period of about 1.4 days, revealing that it was a contact binary. More importantly, the period was decreasing. The orbit was not merely short, it was becoming shorter at an accelerating rate. The light curve also changed shape, showing that the structure of the system was evolving as the stars approached merger. Imagine receiving one brightness measurement after another across several years. At first, the pattern repeats with reassuring regularity. The system dims, brightens, dims again, and completes another orbit. Yet when the timings are compared carefully, each cycle arrives slightly early. The difference is small, but it grows. The stars are circling faster because their separation is falling. Eventually, the repeating pattern becomes harder to distinguish, as material surrounds the system and the geometry changes. Then the source begins a sustained rise in brightness, months before the eruption is formally discovered. The final outburst was not an isolated surprise. It was the visible end of an accelerating process already recorded in the data. V1309 Scorpio remains unusually valuable because astronomers rarely possess such a clear record of a merger progenitor. The system was not observed because anyone knew it was about to become a red nova. It happened to lie within a survey field designed for other purposes. Its ordinary variations were stored alongside vast numbers of other stellar measurements. Only after the eruption did researchers return to the archive and recognize that they had watched the orbital clock run faster and faster. This is one reason repeated sky surveys are so powerful. A measurement that appears routine today may become the opening scene of an event understood years later. Not every shrinking binary will produce the same warning. The orbital signal may be hidden by dust, irregular mass loss, star spots, or the geometry of the system. If the orbit is not aligned in a helpful way, eclipses may be weak or absent. A distant source may be too faint for precise monitoring. Some systems may change slowly for centuries and then enter a rapid plunge between observations. Others may brighten before the orbit becomes impossible to measure. Astronomers therefore search for several signs at once: shortening periods, changing light curve shapes, increasing luminosity, unusual infrared emission, and evidence that gas is leaving through the outer parts of the binary. Once both stars fill or overfill their Roche lobes, they may form a contact binary. In a contact system, the stellar surfaces touch within a shared outer layer, though the denser interiors remain distinct. The pair can resemble a peanut-shaped structure rotating as one connected object. Gas and heat move between the components. The system may still persist for a long time if the transfer and energy flow find a workable balance. Contact does not guarantee an immediate merger. Many contact binaries are observed throughout the galaxy without showing any sign that they will combine tomorrow, next year, or even within a human lifetime. The most familiar class of low-mass contact binaries is often called W Ursae Majoris systems. They usually contain stars sharing a common envelope and orbiting in less than a day. Their surfaces can have similar temperatures even when their masses differ, because energy is transferred through the shared layers. They're common enough to show that contact itself is not an instant death sentence for a binary. Yet some contact systems continue losing angular momentum, develop extreme mass ratios, or enter unstable mass transfer. Their temporary balance then fails. A very low mass ratio can create serious difficulties. The smaller star may no longer orbit in a stable way outside the larger star's envelope. Mass leaving through an outer Lagrange point can form a stream or ring around the binary and carry substantial angular momentum away. Because that angular momentum comes largely from the orbit, the separation decreases further. The faster the orbit shrinks, the stronger the overflow can become. This feedback turns a gradual interaction into an accelerating spiral. The system may spend years displaying measurable changes, then cross into a phase that unfolds over months, weeks, or even days. Gas lost through the outer Lagrange regions does not necessarily escape in every direction equally. Rotation favours the orbital plane, so material can form a flattened or spiral-shaped outflow around the binary. Each new turn of the orbit lays down more gas. rather like a rotating garden sprinkler, except the sprinkler contains stellar plasma and would be discouraged by every reasonable safety authority. Later, ejecta from the merger can collide with this previously lost material. The density and shape of the early outflow therefore influence the future red nova's brightness, spectra, and appearance from different viewing angles. As matter leaves, it can cool enough to form molecules and eventually dust. This may begin before the main luminous outburst, hiding the binary at visible wavelengths while increasing its infrared glow. The dust absorbs shorter wavelength radiation and re-radiates the energy as infrared light. To an observer using only ordinary visible images, the system may seem to fade or disappear just as the physical interaction is intensifying. Infrared telescopes can reveal that the missing light has not vanished. It has been processed by surrounding material. The stars themselves are also being altered. The donor's outer layers are stripped and disturbed. The accretor is heated and spun up. Circulation within the shared envelope transports energy. The orbital plane may become surrounded by dense gas, while lower density regions develop above and below it. Magnetic fields are twisted by differential rotation. None of this happens in perfect symmetry. Three-dimensional flows create streams, shocks, eddies, and temporary concentrations of matter. Simplified diagrams often show two tidy teardrop-shaped Roche lobes and one elegant stream through L1. They are useful, but the actual system would make the diagram look as though it had experienced a difficult afternoon. Eventually the distinction between orbit and atmosphere begins to break down. The companion is no longer moving through nearly empty space around the donor. It is moving through gas. That gas exerts drag. Gravitational wakes form behind the moving stellar core, pulling backward on its motion. Orbital energy is transferred into the envelope, heating it and pushing some of it outward. The companion loses speed relative to the orbit it once followed and drops deeper into the donor's extended layers. The inward spiral accelerates. This transition is the entrance to common envelope evolution, but it may not occur at one perfectly defined instant. The system can pass through contact, unstable mass transfer, heavy outflow, and partial engulfment. For a while, astronomers may debate whether it should be called a deep contact binary, an early common envelope, or a merger already in progress. The gas does not care which phrase we choose. What matters physically is that the two stellar cores are now embedded within material that interacts strongly with their motion. The amount of energy available from the shrinking orbit is enormous. Bringing two stellar masses close together makes their gravitational binding stronger, releasing orbital energy. If enough of that energy reaches the surrounding envelope efficiently, it may unbind the gas and eject it from the system. The cores could then survive as a much tighter binary. If the envelope is too massive, too tightly bound, or too difficult to eject, the cores continue inward and merge. These two outcomes, survival or coalescence, make the common envelope phase a decisive turning point in binary evolution. For a luminous red nova, we're especially interested in systems where the inward motion leads to a merger, or to a violent envelope ejection event closely associated with one. Yet the final bright display is built from everything that happened during the approach. The period decline tells us how quickly orbital energy and angular momentum were being lost. The pre-outburst mass loss creates material for later shocks. The shape of the binary determines where gas is concentrated. The stellar structures determine whether the envelope can be removed. By the time the stars are fully engulfed, the coming outburst has already acquired much of its character. The slow spiral, then, is not simply two stars tracing smaller and smaller circles. It is a coupled evolution of orbit, spin, mass, heat, and gas flow. One star expands because its core has changed. Its surface reaches the Roche boundary. Matter crosses toward the companion. The stars respond by changing size and rotation. Some gas remains, some escapes, and the escaping portion carries motion away. Tides pull angular momentum from the orbit. The separation falls, contact deepens. A shared outer layer develops, and each orbit takes place inside an environment denser than the one before it. From a distant telescope, the system may still appear as one unresolved dot. Its brightness rises and falls, and those variations provide the only visible hint that two stars are struggling inside. The period shortens by tiny amounts, the shape of the signal changes, infrared emission grows. Then, as the surrounding gas becomes thicker and the orbital motion becomes harder to trace, the neat repeating rhythm disappears. The binary has crossed from two stars exchanging material across a narrow bridge into two stellar cores moving through one extended atmosphere. That shared atmosphere changes the physics immediately. Calling this a common envelope can make it sound almost peaceful, as though the stars have agreed to share a blanket. In practice, the arrangement is unstable and extremely complicated. The companion pushes through material that was once part of the giant star's outer layers. Gas piles up ahead of it, flows around it, and trails behind in a dense gravitational wake. That wake pulls backward on the companion, creating drag. The drag removes orbital energy and angular momentum, so the companion cannot remain at the same distance from the core. Its orbit shrinks, its speed and surrounding conditions change, and the inward motion can accelerate into what researchers often call the dynamical plunge-in. There are two related kinds of drag involved. Ordinary hydrodynamic drag comes from physically moving through gas, rather like an object pushing through water, although the scale and temperatures here are beyond anything familiar. Gravitational drag can be even more important. The companion's gravity focuses gas into an overdense wake behind it, and the attraction of that wake slows the companion. This process is sometimes called dynamical friction. The lost orbital motion does not disappear. It becomes heat, turbulent movement, shocks, rotation, and large-scale expansion within the envelope. Each orbit therefore changes the environment for the next one. The companion launches spiral disturbances through the gas. These waves can steepen into shocks, carrying energy and angular momentum away from the central orbit and into more distant layers. Material in the envelope begins to rotate faster. Some regions are heated and pushed outward. Other regions remain gravitationally bound and may later fall inward again. The flow is strongly three-dimensional, with streams crossing, shocks wrapping around the stellar centers, and denser matter often collecting near the orbital plane. Even a computer designed specifically for this problem can find the whole arrangement rather impolite. At the center of the giant star is a compact core that may contain a substantial fraction of the star's mass within a small volume. Around it lies the much more extended envelope. That envelope can be enormous in radius while remaining relatively diffuse in its outer regions. The companion first encounters those low-density layers, but as it travels inward, the surrounding density generally rises. The drag becomes stronger, and the amount of orbital energy released per change in separation increases. The deepest part of the spiral can therefore unfold far more rapidly than the earlier approach that brought the system into contact. The word rapidly is relative. The star may have spent millions of years evolving toward this condition, yet the main plunge through the envelope can occur over a timescale of only several or dozens of orbits in many simulations. Depending on the size of the giant in the original period, that could mean months, weeks, or even shorter intervals for the most dynamic part of the interaction. The system crosses from slow stellar evolution into a hydrodynamic event. It is no longer enough to calculate only how the stars change internally. One must follow gas motion, shocks, gravity, rotation, radiation, and energy transport together. The central question is whether the released orbital energy can remove the envelope before the two dense centers merge. The envelope is held to the giant by gravity, so unbinding it requires energy. As the companion falls closer to the core, the orbit becomes more tightly bound and releases energy. If a sufficient fraction of that energy reaches the envelope in a useful form, gas can be accelerated beyond the system's escape speed. The star then loses much of its outer atmosphere, leaving the original core and the companion in a much tighter orbit. If the transfer is inefficient, or if the envelope is too strongly bound, the companion continues inward, and the stellar centers may combine. Astronomers often describe this problem with an energy calculation called the alpha formalism. In its simplest form, it compares the change in orbital energy with the binding energy of the envelope. A parameter usually written as alpha represents how efficiently the released orbital energy contributes to envelope ejection. Another quantity, lambda, summarizes how tightly the envelope is bound according to the giant star's internal structure. This approach is useful for estimating possible outcomes across enormous populations of binary stars, but it compresses a complicated three-dimensional event into a few numbers. It can tell us whether an outcome seems energetically plausible, without showing exactly how the gas finds its way out. The envelope is not bound equally at every depth. Material near the outer edge may require relatively little energy to escape. Gas closer to the core sits in a deeper gravitational potential and is harder to remove. The internal energy of the envelope also matters. Hot ionized gas stores energy in the arrangement of its electrons and nuclei. As the expanding material cools, electrons can recombine with ions, releasing recombination energy. Researchers continue to examine how much of that energy helps accelerate the envelope and how much escapes as radiation. In several modern simulations, including calculations that follow giant star envelopes in 3 dimensions, recombination energy substantially assists expansion and can be important for achieving near-complete ejection. It may help to imagine the envelope as a large structure that is already close to being loosely attached in its outer regions. The companion does not need to blast every atom outward in one clean explosion. Instead, repeated orbital passages stir and expand the gas. Spiral shocks carry energy through it. Rotation reduces the effective gravitational hold in some regions. Recombination adds energy as the material cools. Gas can leave in stages, with some escaping early, some after further heating, and some remaining bound for a longer time. What appears from a distance as one outburst may be the combined light from several linked episodes. The direction of the escaping matter is not necessarily spherical. Because the energy and angular momentum originate in an orbit, the flow often remembers the orbital plane. Dense material may be driven outward around the equator, forming a flattened structure, while lower density regions develop toward the poles. Spiral arms can extend through the envelope and into the surrounding space. Later, faster ejecta may travel more easily through the polar directions, and then collide with the slower, denser gas nearer the equator. This geometry can strongly affect the light we observe, especially because the same event may look different when viewed from above the orbital plane than when seen through its dusty equatorial material. That asymmetry helps connect common envelope physics with luminous red novae. Before the brightest phase, the binary may already have expelled a slow equatorial outflow. When the plunge-in or final merger launches faster material, the new ejecta catch up with the earlier gas. Their collision forms shocks outside the central system. Energy that began as orbital motion is converted into heat at these shock fronts, and the surrounding optically thick material can absorb and reprocess the radiation. A substantial fraction of the visible display may therefore be produced away from the place where the stellar centers are actually merging. Deep inside the common envelope, direct sight is difficult. The gas can be so optically thick that photons scatter many times before escaping. The energy released near the orbit may be trapped temporarily and carried outward with the expanding material. By the time that energy reaches a layer from which light can escape, the gas may have moved far from the central stars and cooled considerably. This is one reason the visible surface of a red nova can grow to an enormous size. We are not necessarily seeing either original stellar surface. We are seeing a temporary photosphere within the outflow. Convection and turbulence complicate the transport still further. Heating from the shrinking orbit creates buoyant gas. Shearing flows develop where neighbouring layers move at different speeds. Simulations have found spiral shocks and large-scale instabilities that can redistribute energy and angular momentum through the envelope. Some energy may travel outward efficiently, helping to expand distant layers. Some may remain near the orbit or be radiated away. Small differences in how these processes are modelled can change how much gas becomes unbound before the calculation must stop. Accretion onto the companion is another uncertain part of the story. As the companion moves through the envelope, its gravity draws gas toward it. A simple estimate might suggest an enormous accretion rate, but the real flow has angular momentum, pressure, density gradients, shocks, and feedback. Much of the focused gas may be deflected rather than swallowed. If the companion does accrete rapidly, the released gravitational energy could heat the surroundings or help launch jets. Those jets might carve channels through the envelope and assist ejection, particularly along the rotation axis. Their importance probably varies from one system to another and remains an active subject of research. For the ordinary stellar companions involved in many red nova mergers, accretion can also make the receiving star expand. Gas arriving faster than the star can thermally adjust, adds heat and mass to its outer layers. The companion may become bloated until its own surface contributes to the shared envelope. At that stage, the distinction between donor and accretor becomes less useful. Both stars are embedded, both are being distorted, and gas moves through a structure that belongs cleanly to neither one. The two dense centers continue orbiting inside an object whose visible edge surrounds them both. The core of the giant does not behave like a bare solid ball. It is a dense stellar region connected to layers above it, while the companion may also have a core and envelope of its own. As the separation falls, tidal forces become intense. The companion can be stretched, heated, and stripped. If it is much less dense than the primary core, it may begin to break apart before reaching the center. Its material can form a disk or stream around the core. In another system with more comparable stars, the two inner regions may remain recognizable until they come into direct contact. The exact route to merger depends on stellar mass, age, density, and composition. Meanwhile, the orbit may stop shrinking as quickly even before the envelope is fully ejected. The rapid plunge can end when the nearby gas has been spun into partial corrotation with the binary, reducing the relative motion and therefore the drag. The remaining system can enter a slower phase in which additional envelope loss occurs over thermal or longer hydrodynamic timescales. This is one of the reasons simulations can be difficult to interpret. A calculation may complete the rapid plunge while a significant amount of gas remains technically bound. That does not automatically mean the envelope will stay forever. Later expansion, recombination, radiation, winds, or renewed interaction may continue removing it after the simulated interval. Conversely, gas counted as unbound at one moment may encounter other material, radiate energy, or follow a path more complicated than a clean escape. Researchers use different criteria to decide whether a parcel of simulated gas has enough energy to leave permanently. Including only kinetic and gravitational energy gives one answer. Adding thermal and recombination energy gives another. The outer boundary of the calculation and the time at which it is stopped also matter. When different studies report different ejection fractions, part of the disagreement may reflect genuine physical differences, while part comes from how the problem was represented and measured. The required range of scales is extraordinary. A simulation may need to follow a giant envelope hundreds of times wider than the dense stellar core, while also resolving the region around a relatively small companion. The rapid plunge takes only a limited number of orbits, but the slower adjustment after it can last much longer. Gravity, gas dynamics, radiation, ionization, magnetic fields, and possibly jets can all matter. Improving one piece often makes the calculation more expensive. This is why common envelope evolution remains one of the largest uncertainties in predicting the lives of binary stars, despite decades of work and increasingly sophisticated three-dimensional models. Even so, the simulations have revealed a consistent broad picture. The companion enters the envelope and loses orbital energy through drag and gravitational interaction. Spiral shocks and wakes transfer energy and angular momentum into the gas. The envelope expands, becomes asymmetric, and may be partially or largely ejected. The orbit shrinks dramatically. After that, the system either emerges as a close binary stripped of the giant's envelope, or proceeds toward a merger. The unanswered questions concern the efficiency, timing, geometry, and importance of additional energy sources rather than whether the basic exchange occurs at all. For red novae, the merger outcome is the one that draws our attention, but a successful envelope ejection without merger is equally important in the wider universe. It can create close pairs containing a white dwarf and an ordinary star, two stellar cores, or later, a neutron star or black hole with a companion. Some systems that eventually produce Type 1 supernovae, X-ray binaries, or compact object mergers may require an earlier common envelope phase to bring the stars close enough together. Without this sudden orbital shrinkage, many binaries would remain too wide to interact strongly again. A brief hidden episode inside a giant atmosphere can therefore determine events billions of years later. This gives the common envelope a curious place in astronomy. It may be responsible for creating some of the tightest and most dramatic binary systems, yet the event itself is rarely observed directly. The plunge is hidden by the same gas whose behavior we want to measure. Most surviving binaries tell us only the final result. Their current separation, masses, and compositions allow researchers to reconstruct possible histories, but several different paths can lead to similar remnants. Luminous red novae offer a more immediate view because the envelope's disturbance becomes bright enough to announce itself. The light, however, still gives only an indirect report. A rising luminosity may indicate increasing mass loss or shocks. A cool plateau may reflect recombination in expanding hydrogen-rich ejecta. Infrared brightening may reveal dust forming in dense outflows. Spectral lines measure velocities along our line of sight, while the true flow extends in 3 dimensions. Polarization can hint that the ejecta are not spherical. Long-term imaging may eventually resolve surrounding structures. Each observation samples a different part of the envelope's response to the inward-moving stars. Within the system, the two cores may complete orbit after orbit, while the distance between them falls. Suppose the separation is reduced by half. The released orbital energy can be much larger than it was during a similar change farther out because gravity becomes increasingly strong at smaller distances. The gas close to the orbit is heated more intensely. Shocks strengthen. Material is thrown outward with greater speed. At some point, the interaction may change from the relatively extended common envelope plunge into the final coalescence of the stars themselves. The boundary between those stages is not always sharp. In one event, the envelope may be largely expelled before the cores touch, leaving a brief interval in which the exposed objects continue spiraling together. In another, thick gas may remain around them through the entire merger. One companion may be disrupted into a stream. 2 similar cores may make direct contact. A small star may sink deep inside a much larger one and deposit its material gradually. Different routes can all release enough energy to create a luminous red nova, but they shape the timing and brightness in different ways. As the separation becomes comparable to the sizes of the inner stars, the familiar idea of an orbit begins to fail again. Tidal distortion grows extreme. Matter can no longer remain arranged in 2 nearly separate bodies. Gas flows violently across the narrowing gap, and the rotation of the merged structure must somehow accommodate the angular momentum that once belonged to the orbit. Some of that angular momentum is carried away by ejecta. Some remains in the rapidly spinning remnant. Too much rotation can prevent the new object from settling into a simple spherical star, so it may remain enlarged, flattened, unstable, and surrounded by a disk or torus of material. The common envelope has therefore done more than hide the stars. It has prepared the final collision. The remaining distance between the stellar centres is now small enough that the old orbit cannot continue for much longer. Gas surrounds both objects, Drag removes energy with every circuit, and the companion moves through layers that become denser as it travels inward. The two stars may still have recognizable cores, but their outer regions have already been stretched, stripped, heated, and mixed. At this stage, calling them separate stars is becoming less a description of what they are and more a reminder of what they were only a short time earlier. The final merger does not necessarily happen as one clean impact. Stars are not solid objects with hard surfaces. They're enormous bodies of hot gas held together by gravity, with density and pressure increasing toward their centers. Their visible edges are only the levels from which light can escape easily. When their outer layers meet, gas begins interacting before the densest regions touch. Streams move between the stars. Shocks form where flows collide. Material may wrap around one core, fall toward the other, or be thrown away from the orbit entirely. The system can spend several final orbits in a state where it is neither clearly a binary nor fully one star. That last interval can be brief compared with everything that came before. A binary may take billions of years to reach contact, thousands of years to enter unstable mass transfer, and only months or days to complete its final coalescence. Once the companion is deep inside the shared envelope, the drag becomes powerful. The orbit loses energy rapidly. Each reduction in separation releases more gravitational energy than the same reduction would have released farther out, so the process can accelerate. The closer the stars become, the more strongly gravity binds them, and the greater the amount of energy that must be transferred somewhere else. This is one of the central engines of a red nova. The sudden release of energy is not mainly caused by a new type of nuclear reaction switching on throughout the stars. It comes largely from gravity and orbital motion. Two massive objects that were once separated are brought into a much tighter arrangement. Their gravitational potential energy decreases, while energy is deposited into the surrounding gas. Some of it becomes heat, some becomes the kinetic energy of ejecta, some increases the rotation of the merged object. A fraction eventually escapes as the light that allows astronomers to discover the event. Gravity can seem quiet when it holds a star or planet in a stable orbit, but there is a tremendous amount of energy stored in that arrangement. Imagine allowing an object to fall toward Earth. As it descends, gravitational potential energy becomes motion, and then heat when the object is stopped. In a stellar merger, the falling objects are stars. The distances are millions of kilometers, and there is no ordinary ground waiting at the bottom. The orbital motion is instead slowed by gas, shocks, tides, and collisions between moving layers. The released energy spreads through the system, and the shared envelope becomes the place where much of it is deposited. The exact amount depends on the masses and initial separation of the stars. A pair of low-mass stars can produce a modest galactic red nova. A merger involving more massive stars may create an outburst visible in another galaxy. Bringing a companion close to the dense core of a giant can release far more energy than moving it through the giant's thin outer atmosphere. Even so, the light we observe represents only part of the total. A great deal of energy can remain hidden as motion, expansion, internal heat, rotation, or the work required to lift material out of the gravitational field. This explains why the brightest looking event is not automatically the merger that released the most total energy. One system may convert a large fraction of its available energy into radiation that escapes quickly. Another may spend most of the energy accelerating gas or expanding an envelope that remains opaque. The second event could involve a major physical transformation while appearing less spectacular through a visible light telescope. The universe, rather inconsiderately, does not provide itemized receipts. As the stellar centers approach, tides distort both objects severely. Their shapes become elongated along the line connecting them. Gas near that line can be pulled away and transferred rapidly. If one star is much smaller or less dense than the other, it may be disrupted before its core reaches the center of the larger star. Material from the disrupted companion can form a thick stream around the primary core. Part of that stream may settle into a disc-like structure, while part plunges inward or is flung outward by rotation. In a system with more similar stars, both inner regions may remain coherent for longer. They can orbit within the common envelope until their outer layers overlap deeply and the cores finally coalesce. The merger may then involve strong shear, meaning neighbouring layers move past one another at very different speeds. Shear converts ordered orbital motion into turbulence and heat. It can also amplify magnetic fields, mix material that once belonged to different depths, and make the remnant rotate unevenly from one layer to another. There is no requirement for the merger to occur symmetrically. The companion may approach through one side of the primary's envelope. Streams may wrap around the centre. Gas may be ejected more efficiently near the orbital plane, while other material escapes above and below it. The remnant can be displaced slightly within its own expanding envelope. A neat picture of two perfect spheres becoming one perfect sphere would be easier to draw, but it would leave out most of the important physics. During the last plunge, pressure waves and shocks travel outward through the gas. A shock forms when material is forced to slow, compress, or change direction faster than ordinary sound waves can communicate the disturbance. The gas behind the shock is compressed and heated. At first, this energy may be trapped because the surrounding envelope is extremely opaque. Photons cannot travel directly outward. They scatter repeatedly from particles and atoms, taking a long, indirect route toward the surface. Because of that trapping, the moment of greatest energy released near the centre does not have to match the moment of greatest visible brightness. Energy can be deposited within the envelope and emerge later, after the gas has expanded or after photons have diffused outward through less dense layers. The observable red nova is therefore delayed and reshaped by the material around the merger. Telescopes do not watch the central collision directly. They watch the envelope respond to it. Some gas is accelerated immediately. Matter, already near the outer parts of the common envelope, requires less energy to escape, so it may be pushed away first. Deeper layers are more tightly bound and need a stronger transfer of energy. The result can be several episodes of mass loss rather than one uniform shell. Slow material may have left during the unstable mass transfer phase. A faster shell may be launched during the dynamical merger. Additional gas may be removed as the remnant expands and readjusts afterward. These different outflows can collide. The slow material expelled before the merger has a head start, but the later ejector move faster. When the faster gas catches the earlier flow, kinetic energy is converted into heat at the collision front. If the surrounding matter is dense enough, that heat is radiated efficiently and can contribute substantially to the luminosity. This provides one explanation for why many luminous red novae display more than one peak in their light curves. The first peak may be connected with hot ejector expanding and releasing stored thermal energy. A later, broader peak can be powered partly by shocks, as faster material encounters dense gas that was placed around the system before the final merger. Recombination within the cooling ejector can also help maintain the later emission. These processes can overlap, and their relative importance is still being studied. A light curve that looks like two simple hills on a graph may represent several layers of gas, launched at different times, moving at different speeds, and repeatedly converting one form of energy into another. The geometry of the pre-existing material matters here. Gas lost from a rotating binary tends to become concentrated around the orbital plane. It may form a spiral or a thick equatorial structure. Later ejector can expand more freely toward the poles, where there is less matter in the way, but collide strongly with the dense equatorial gas. The event can therefore develop a bipolar or hourglass-like shape, even if the earliest visible image is only an unresolved point. Seen from one direction, an observer might look down through a relatively clear polar region and detect hotter radiation from deeper layers. Seen from the side, the same event may be hidden behind dense gas and dust near the equatorial plane. The measured brightness, colour and spectral features can depend partly on viewing angle. Two mergers with similar physical energies might appear different simply because one presents a clearer route for its light to escape. Angular momentum creates another major problem during the final merger. Before contact, a large amount of angular momentum is stored in the orbit. Once the stars become one object, that motion cannot vanish. Some angular momentum leaves with ejected gas. Matter thrown from the outer regions can carry a disproportionate amount because it is moving far from the rotation axis. The rest remains within the remnant, causing it to spin rapidly. If all the original orbital angular momentum were placed into a compact spherical star, the surface might rotate too quickly to remain gravitationally bound. Material at the equator could be thrown off. The remnant, therefore, has to redistribute or lose angular momentum as it forms. Gas can move outward into a disk or torus. Magnetic stresses can transfer rotation between layers. Winds can carry angular momentum away over longer periods. The merged star may remain enlarged, partly because a larger object can accommodate the rotation more easily than a compact one. The remnant is unlikely to rotate like a solid wheel. Its inner and outer layers can turn at different rates. This differential rotation stores additional energy and may drive mixing and magnetic activity. Material from the companion can be carried deep into the primary, while gas from the primary's interior may be pushed outward. The chemical structure inherited from two separate stars becomes rearranged. The final star is not simply the larger component with the smaller one placed neatly inside. It is a new object with a complicated internal history. The collision can introduce fresh hydrogen-rich material into regions where it was not previously present. It can alter convection, which is the movement of hot gas upward and cooler gas downward. It may rejuvenate parts of a star by mixing fuel into layers that had begun to exhaust it. In some cases, a merger product can appear younger or more massive than nearby stars formed at the same time. Objects known as blue stragglers, for example, are often explained through mergers or mass transfer, although not every blue straggler is produced in exactly the same way. A red nova remnant may initially look nothing like a settled blue straggler. Immediately after the event, it is expected to be swollen, cool at the surface, rapidly rotating and surrounded by ejecta. Its interior contains excess thermal energy. The outer layers may extend to hundreds or even thousands of times the sun's radius in some events. Dust can conceal it. The remnant then has to contract, radiate energy, redistribute angular momentum, and find a new internal equilibrium, a process that can take years, decades, or much longer depending on its mass and structure. The final merger itself may also release energy through accretion. If material from one star forms a stream or disk around the core of the other, it falls deeper into the gravitational field before settling. That infall converts gravitational energy into heat. In some systems, accretion may help launch jets. Fast, narrow outflows from near the central object could drill through parts of the envelope and contribute to mass ejection. How important jets are in ordinary red novae remains debated, and they may be essential in some mergers while playing a small role in others. Magnetic fields could become much stronger during the coalescence. The original stars already possess fields, and the violent differential rotation of the merged gas can stretch and twist them. Turbulence may amplify them further. Strong fields can transport angular momentum and influence later winds or jets. Yet the central region is hidden, so astronomers often have to infer these processes indirectly from the shape, polarization, or later activity of the remnant. Nuclear fusion does continue inside the stars during all of this, but it is not responsible for the main explosive display in the way that thermonuclear burning powers a classical nova. The ordinary fusion taking place in the stellar cores cannot suddenly respond fast enough to account for the observed outburst. There may be localized changes if fresh material is mixed into hot regions, but the immediate reservoir is overwhelmingly gravitational and orbital. The red nova is a gravity-powered transient shaped by gas dynamics. That distinction also separates it from a core collapse supernova. In a supernova, a massive stellar core loses support and collapses, releasing an extraordinary amount of gravitational energy and producing a neutron star or black hole. The explosion can accelerate several solar masses of ejecta to thousands or tens of thousands of kilometers per second. A red nova is slower and less energetic. The central star does not usually undergo catastrophic core collapse. Its outer structure is reorganized because of a companion, and a stellar object remains at the center afterward. The ejecta velocities from red novae are commonly measured in hundreds of kilometers per second, rather than the much greater speeds typical of supernovae. That is still extremely fast. At 100 kilometers per second, material would cross the distance between London and Edinburgh in only a few seconds, which would be impressive but not especially helpful for the railway timetable. Across space, that gas can travel billions of kilometers in months and continue expanding for years. The speed often reflects the escape velocity from the region where the material was launched. Gas removed from the outer layers of a giant may leave more slowly because gravity is weaker there. Material accelerated closer to a compact stellar core can reach higher speeds. Observing several velocity components can therefore reveal that mass was expelled from different depths or at different stages. Narrow spectral lines may trace slow surrounding gas, while broader features reveal faster ejecta from the final merger. The amount of material lost also varies. A low-mass contact binary may eject only a modest fraction of a solar mass. A massive merger involving an evolved star can throw out much more. Not all expelled gas escapes permanently. Some may rise outward, lose energy, and fall back toward the remnant. Falling material can form a disk, produce additional heating, or drive later episodes of activity. The aftermath can continue changing long after the main visible peak has faded. Fallback makes the boundary between merger and remnant especially untidy. Matter that seemed to be leaving may return months or years later. The remnant may brighten irregularly as gas settles. Dust formation can hide these changes in visible light, while infrared observations reveal continuing energy. A red nova is not a single flash, followed by immediate calm. It is the brightest portion of a much longer reorganization. During the final coalescence, the stellar surface may expand rapidly as energy moves outward. Heated gas requires greater pressure support and occupies more volume. The envelope is also lifted by the mechanical energy deposited through shocks and orbital decay. As the radiating layers move outward, the temporary photosphere grows. Its radius can increase even while the gas temperature begins to fall. A larger surface can emit a large total amount of light despite being cooler per square meter than it was earlier. This is an important idea because our everyday experience tends to connect brightness only with temperature. A small hot object can shine strongly, but so can a much larger cooler one. A red nova becomes luminous partly because the radiating area grows to an extraordinary size. At first, the emission may appear relatively blue as hot ejecta become visible. Later, expansion and cooling shift the light toward red and infrared wavelengths. The event seems to change personality, though it is really one evolving outflow viewed at different stages. The first photons to escape do not carry a straightforward film of the collision. They have been scattered, absorbed, and re-emitted many times. Spectral lines are broadened by moving gas. Radiation from the central remnant is processed by the envelope. Shock energy is released at varying distances. Dust begins blocking some wavelengths while emitting at others. Astronomers reconstruct the merger by comparing the changing light with models of expansion, radiation transport, recombination, and circumstellar interaction. A rapid initial rise in brightness may indicate that a hot shell has reached a point where radiation can escape. A broad later maximum may show that shocks are operating within dense material, or that recombination is controlling the release of stored energy. A plateau can form when the receding recombination front maintains a roughly steady, effective temperature as the ejecta expand. Infrared brightening indicates that dust or very cool gas is becoming important. No single measurement reveals the whole engine, but the sequence allows researchers to work backward. The energy release is therefore sudden in one sense and delayed in another. The orbital plunge may deposit much of its energy over only a few dynamical times, yet the envelope can store that energy and reveal it over weeks or months. Shocks can add luminosity later when shells collide. Recombination releases internal energy as ions regain electrons. The remnant continues radiating as it contracts. What observers call the outburst is an extended response to a brief central transformation. There may not even be one exact instant at which astronomers could say that the two stars became one. Their outer layers merged first. One core may have been disrupted gradually. Material could orbit the remaining core before settling. The remnant may retain two concentrations temporarily before they fully mix. In a fluid object, identity fades through a process rather than ending at one clearly marked boundary. The stars become increasingly inseparable until no stable orbit remains between them. V1309. Scorpii offered a rare observational view of this transition. Its orbital period shortened for years, its repeating contact binary signal disappeared, and the system brightened. After the 2008 eruption, the original binary variation did not return. The evidence indicated that the two stars had coalesced. Infrared observations later revealed a cool, dusty remnant, showing that the event had created a new object hidden within its own expelled material. Other red novae involve more massive and distant systems, so their final mergers cannot be monitored with the same detail. Researchers compare their pre-outburst luminosities, light curves, spectra, velocities, and late remnants to determine whether the same broad process occurred. The diversity is expected. A merger between two low-mass main sequence stars is not identical to one involving an evolved giant and a smaller companion. Their envelopes have different structures, their orbital energies differ, and the amount of surrounding gas can vary enormously. Despite those differences, the same basic conversion lies beneath them. Orbital separation is lost. Gravitational energy is released. Angular momentum is carried outward. Gas is heated and accelerated. The separate stellar structures are replaced by a rotating remnant and expanding ejecta. The light appears because some portion of that energy finds its way through the surrounding material and into space. By the time the central merger is complete, the scene is still far from settled. A single swollen remnant turns rapidly inside an expanding envelope. Slow gas from the earlier mass transfer phase occupies the surrounding region. Faster shells from the final plunge move into it. Shocks continue converting motion into heat. Ionized material expands away from the center, carrying stored energy with it. The photosphere grows outward through the ejecta, and the temperature begins changing as the same energy is spread across an increasingly large volume. The newly merged object is still surrounded by the material thrown outward during the final plunge. Close to the center, gas remains hot, compressed, and difficult to see through. Farther away, earlier outflows are already spreading into space. Between them lies a temporary radiating surface that can grow to a size far larger than either of the original stars. This expanding surface is one of the main reasons a luminous red nova changes so dramatically after its first brightening. It may begin with relatively hot, pale or blue-white light, but over the following weeks and months, its temperature falls, its visible color shifts, and much of its energy moves into the infrared. The outburst becomes red not because someone has adjusted a cosmic color setting, but because the gas is expanding, cooling, recombining, forming molecules, and eventually producing dust. Expansion begins as soon as the merger transfers enough energy and momentum into the surrounding envelope. Shocks push through the gas, pressure rises, and material starts moving away from the central remnant. Some layers may travel at only a few tens of kilometers per second, while others reach several hundred kilometers per second or more. Those numbers sound modest beside the ejecta of a supernova, but they are more than enough to enlarge the system rapidly. Gas moving at 100 kilometers per second travels more than 8 million kilometers in a day. After several weeks, the outflow can occupy a region comparable in scale to the orbit of a planet. Nothing solid is inflating. countless particles are simply moving outward together, carrying heat, motion, and radiation with them. As the gas expands, it has to work against gravity and against the surrounding material. It also does work on itself by pushing neighbouring layers outward. Energy that was once stored as heat becomes part of the motion and expansion of the ejector. Physicists describe much of this cooling as adiabatic expansion. The term sounds slightly unfriendly, but the idea is straightforward. When a gas expands without receiving enough new heat to replace the energy it spends, its temperature drops. The same basic effect occurs when compressed gas is released from a container, although a stellar envelope is a rather larger demonstration and should not be attempted in the kitchen. The density falls at the same time. A fixed amount of matter now occupies a larger volume, so the particles become more widely separated. Collisions occur less frequently. The pressure decreases. The gas becomes less capable of maintaining the high temperatures found near the merger. Radiation trapped within it also loses energy, as the expanding material stretches the wavelengths of the photons through repeated interactions. This combination of mechanical expansion, declining density, and radiation loss pushes the outflow toward cooler conditions. At first, however, the gas can remain opaque. Opaque does not necessarily mean completely dark. It means photons cannot travel directly through the material without being absorbed or scattered. A photon created near the central remnant may encounter an electron, an atom, or an ion, change direction, travel a short distance, and collide again. Instead of taking a straight journey outward, it performs something closer to an extremely inefficient walk through a crowded room. By the time the energy finally reaches space, the gas that first produced it may have expanded far beyond its original location. The surface astronomers observe is therefore not a permanent physical boundary. It is called the photosphere, the layer from which light has a reasonable chance of escaping without many further interactions. As the density and opacity change, the photosphere can move through the ejector. Early on, it may lie within hot material relatively close to the remnant. Later, it may appear at a much larger radius, because expanding gas remains thick enough to hide everything beneath it. The measured photospheric radius can grow even though every individual parcel of gas is continuing outward independently. This creates a useful but slightly counterintuitive result. The temperature can fall while the total luminosity remains high or even rises. Luminosity depends on both temperature and radiating area. A small, very hot surface can emit a great deal of energy, but so can an enormous surface at a lower temperature. During a red nova, the photosphere may expand by a large factor. Each square meter emits less energy as it cools, yet there are far more square meters contributing. The event can remain conspicuous while transforming from a compact hot source into something resembling an oversized cool supergiant. Observations of luminous red novae repeatedly show this general evolution. Early spectra can display a blue continuum and hydrogen emission, suggesting relatively hot ionized gas. Around later maxima or plateau phases, the inferred temperature often falls toward roughly 5,000 or 6,000 Kelvin. During the subsequent red phase, it can decline to approximately 3,000 or 4,000 Kelvin, while the spectrum begins to resemble that of a late-type giant or supergiant. In the recently observed red nova AT2025a BAO in the Andromeda Galaxy, for example, the photospheric radius increased while the temperature fell, and later spectra developed strong molecular absorption associated with cool gas. Colour is closely tied to temperature because hot material emits a different distribution of wavelengths from cool material. A very hot photosphere releases a large fraction of its visible energy toward blue wavelengths and produces substantial ultraviolet radiation as well. As the temperature drops, the peak of the emission shifts toward longer wavelengths. Yellow and red light become relatively stronger, followed eventually by near-infrared emission. The source is not producing only one colour. It emits across a broad spectrum, but the balance changes, allowing astronomers to describe it as becoming progressively redder, The word crimson is therefore a convenient description, rather than a promise that every red nova would look like a perfectly coloured red lamp to human eyes. Its apparent colour would depend on temperature, dust, distance, interstellar extinction, and the sensitivity of the observer. Many red novae are too distant or too faint to show obvious colour without telescopes and filters. Astronomers measure the brightness through several wavelength bands and compare them. When the source fades more quickly in blue filters than in red or infrared filters, the measurements reveal the same shift that an eye might describe as deepening red. Hydrogen recombination helps explain why the cooling can produce an extended bright phase rather than an immediate disappearance. Soon after the merger, much of the hydrogen-rich ejecta is ionized. Its electrons have been separated from their atomic nuclei by heat and energetic radiation. As the temperature falls, electrons begin rejoining protons to form neutral hydrogen atoms. This transition releases energy that had been stored in the ionized gas. Recombination does more than add a little extra radiation. It also changes the opacity. Free electrons scatter photons efficiently, helping to keep the ejecta opaque. When electrons become bound inside neutral atoms, the number of free electrons decreases and the gas becomes more transparent. A recombination front can move inward through the expanding material in mass coordinates, separating cooler neutral gas outside from hotter ionized gas deeper within. Light escapes from near this moving front, and the effective temperature can remain within a relatively narrow range for some time. This is similar in broad principle to the recombination-powered plateaus observed in some hydrogen-rich supernovae, although red novae involve lower energies, lower speeds, and a different central event. Models of luminous red novae have shown that hydrogen recombination can help power broad red peaks or plateau-like phases while regulating the release of radiation from the expanding ejecta. The exact contribution differs among events, and shocks may supply additional or even dominant energy in some cases. Think of the ionized envelope as containing a temporary store of internal energy. The merger heated and disturbed the gas. Expansion begins draining that energy, but recombination returns part of it as radiation and heat, while the temperature passes through the appropriate range. At the same time, the decrease in opacity allows previously trapped photons to escape more easily. The result can be a broad period of sustained brightness rather than a brief flash followed by darkness. The front does not sit at one fixed distance from the remnant. The gas itself is expanding outward, while the location at which hydrogen recombines moves through layers of differing density and temperature. The visible photosphere may therefore remain associated with a similar recombination temperature, even as its radius and the physical material beneath it change. From Earth, the source can look as though it has developed an enormous cool surface. In reality, that surface is a changing boundary within moving ejecta. Shock heating complicates the picture in a useful way. Before the final merger, the binary may have expelled slow gas around its orbital plane. The dynamical coalescence then launches faster material. When the fast ejecta catch the earlier flow, a shock converts kinetic energy into heat. Dense gas behind the shock cools by radiation, creating an additional source of luminosity. This interaction can help produce a second maximum that is broader, cooler, and redder than the first. The shocks may also compress the gas into thin, dense regions. High density encourages rapid cooling because particles collide frequently, and energy can be radiated efficiently. Once the temperature has dropped enough, these compressed layers can become good locations for molecule and dust formation. The equatorial material is particularly important, because it may be much denser than the outflow toward the poles. A red nova can therefore build its dusty surroundings through the same collisions that help power its later light. As the temperature falls below the level at which many molecules are quickly broken apart, atoms begin forming stable combinations. Titanium oxide and vanadium oxide can create broad absorption features in visible spectra. Carbon monoxide and water vapor can influence infrared wavelengths. These molecular bands are familiar from the coolest ordinary stars, brown dwarfs, and planetary atmospheres. but their appearance in a recent stellar merger tells astronomers that parts of the expanding envelope have reached surprisingly low temperatures. A spectrum with strong molecular absorption does not look like a simple smooth rainbow. Certain wavelength ranges are absorbed by large numbers of molecular transitions, leaving wide valleys and complicated bands. As these features strengthen, the source may be classified as resembling an M-type star or, in extreme cases, something cooler. V1309. Scorpio evolved toward progressively later spectral types after its outburst, and became hidden increasingly by dust, while other red novae have shown the same movement from hot early spectra to very cool molecular ones. Molecule formation is an important step toward dust, but dust grains require more than a low average temperature. The gas must contain suitable elements, remain dense enough for atoms and molecules to collide, and be shielded from radiation that would immediately destroy small grains. Different materials condense at different temperatures. In oxygen-rich gas, aluminium-bearing compounds can begin forming before silicate grains become stable at lower temperatures. Carbon-rich environments follow different chemical paths. The first grains are extremely small. Atoms or molecules meet and remain attached, creating clusters. If those clusters survive long enough, more material gathers on them. The process can be difficult because a tiny cluster loses heat and responds strongly to radiation. Many early clusters may break apart, yet inside dense, cooling merger ejecta, enough can survive to produce a growing population of solid particles. Studies of V838 Monocerotis have found evidence for changing dust composition after its 2002 eruption, including a condensation sequence in which alumina-like material was followed by silicate formation as the surroundings cooled. Once dust forms, the apparent redness can increase sharply. Dust grains absorb and scatter short wavelengths more effectively than long ones. Blue and visible photons from the central remnant are removed from our direct line of sight, while red and infrared photons pass through more easily. This is related to the reason sunsets on Earth often look red, although the dust around a stellar merger is far denser and is not accompanied by anyone taking a pleasant photograph from a beach. Absorbed energy does not cease to exist. A dust grain warms and re-radiates the energy, mainly at infrared wavelengths determined by its temperature. The visible source can fade dramatically while the infrared source remains bright. To an optical telescope, the event may appear to be ending. To an infrared telescope, it has simply changed departments. The merger continues glowing behind its dusty envelope, and much of its luminosity can only be measured by instruments sensitive to wavelengths longer than the human eye can detect. M85, OT 2006-1 provided a clear example of this redwood evolution. 6 months after its eruption, infrared observations found a strong excess consistent with warm material at a temperature of roughly 1000 Kelvin. Similar infrared behavior had already been associated with V838 Monocerotis and other members of the class. These observations helped establish that the transition from optical light into a cool infrared source was a defining part of luminous red nova evolution, rather than an unusual habit of one object. The dust can be newly formed in the ejecta, but some infrared light may also come from older material that surrounded the system before the merger. A flash of radiation heats distant pre-existing dust, which then emits an infrared echo. Separating freshly condensed dust from an echo requires observations over time, measurements of temperature, and sometimes spatially resolved images. If the emitting region seems too large for newly ejected gas to have reached it, an echo becomes a likely explanation. Geometry again affects what we see. A dense equatorial torus can hide the remnant from an observer viewing near the orbital plane, while polar openings allow more direct light to escape in other directions. Dust grains can scatter photons into our line of sight, polarize the light, and create uneven nebular structures. The object may look faint optically, not because the central remnant has become weak, but because the surrounding dust has placed itself in an inconvenient location. This makes the true luminosity difficult to estimate. Astronomers must combine observations across visible and infrared wavelengths to count as much of the escaping energy as possible. Measuring only visible light after dust formation would underestimate the source badly. The energy distribution may extend from the optical through the near-infrared and into the middle or far infrared, with different components corresponding to the warm remnant, hot newly formed dust, and cooler material farther away. Long-term studies show that the infrared phase can persist for years or decades. Several luminous red nova survivors have faded below the brightness of their progenitors at visible wavelengths, while remaining detectable in the near and mid-infrared. Their remnants can resemble expanded cool stars, sometimes accompanied by dust at temperatures of a few hundred Kelvin. This persistence shows that the end of the optical outburst is not the end of the physical event. The merged star and its surroundings continue releasing stored energy and rearranging themselves long after ordinary surveys have stopped calling the source bright. The expanding gas does not cool at one uniform rate. Dense clumps can remain warmer or become cooler than their surroundings depending on their ability to trap and radiate energy. Shocks may reheat some regions. Radiation leaking from the remnant warms dust from inside. Faster polar ejecta experience different conditions from the dense equatorial flow. A single temperature fitted to the observations is therefore a useful summary rather than a full map of the system. That is why spectra can sometimes appear to contain several temperatures at once. The optical light may resemble one class of cool star, while molecular absorption suggests even colder gas. Warm dust contributes at one set of infrared wavelengths, and colder dust adds another component farther into the infrared. We are observing an unresolved structure containing a hot central remnant, cooling ejecta, compressed shocked gas, molecules, and dust spread across different distances. The photosphere can also appear to shrink later, even though the ejecta continue expanding. Early in the event, opaque material at large radius defines the visible surface. As recombination and dilution reduce the opacity, that outer gas becomes transparent. The effective photosphere then moves inward to slower or denser material closer to the center. The measured radius declines, not because the expanding shell has reversed direction, but because we can now see through it. It is a little like fog clearing from the outside of a landscape, revealing a smaller object that was always hidden within. Eventually, the optical light may begin to reveal the merged remnant again, although dust can delay that view for a very long time. The remnant itself may remain much larger and cooler than an ordinary star of the same mass because it contains excess heat from the merger. As it radiates that heat, it can contract gradually. Its effective temperature may rise again over time, or further mass loss may keep it cool. Rotation, magnetic activity, continued accretion and fallback material can produce additional changes. No two red novae follow precisely the same route through this evolution. A low-mass merger may cool and fade relatively quickly. A massive system with several solar masses of ejecta may stay bright for months and remain hidden in infrared emission for years. One event may form dust almost immediately. Another may show a long molecular phase before a strong dust signature appears. The balance between expansion cooling, recombination, shock interaction, and continuing power from the remnant determines the shape of each light curve. Even the familiar double-peaked pattern is not universal. Some objects show several maxima, broad shoulders, or irregular changes. Each rise can correspond to a new energy source becoming visible, another shell collision, a change in opacity, or renewed mass ejection. A red nova is not required to follow one convenient template simply because astronomers would like to compare it with a graph. The shared characteristics are the overall cooling, reddening, relatively slow ejecta, molecular development, and common appearance of dust after a stellar merger. Yet the broad sequence remains understandable. The merger launches and heats gas. Expansion converts internal energy into motion and reduces the temperature. The photosphere grows because opaque ejecta spread outward. Hydrogen recombines, releasing energy and lowering the opacity. Shocked shells add more heat at larger distances. Molecules survive in the cooling layers. Dust grains condense, absorb visible light, and re-radiate it in the infrared. What began as a hot stellar disturbance becomes an enormous cool envelope surrounding a single unsettled remnant. The red colour is therefore not a separate decoration added at the end. It is a physical record of the changing gas. It tells us that the radiating surface has expanded. It tells us that the temperature has fallen. Molecular bands reveal conditions cool enough for atoms to remain joined. Infrared emission shows that solid grains have formed, or that older dust has been heated. The outburst colour allows astronomers to follow material that cannot be touched, resolved easily, or visited. Among all the systems that have displayed this transformation, one became especially famous. In January 2002, the point of light now known as V838 Monocerotis began behaving in a way that did not fit the usual expectations. It lay in Monoceros, a constellation whose name means the unicorn, roughly in the direction of the outer Milky Way. Before the event, the source had attracted little attention. Then it brightened rapidly enough to be reported as a possible nova, which was a sensible first guess. A previously faint star had appeared to flare, and ordinary novae were already familiar to astronomers. Yet as observations accumulated, this object refused to follow the expected path. It brightened more than once, became cooler instead of developing into the hot, thinning remnant of a classical nova, and transformed into something resembling an enormous red supergiant. The object was not simply unusual in one detail. Almost every new measurement seemed to remove it farther from the category in which it had first been placed. The name V838 Monocerotis is less mysterious than the object itself. Variable stars in each constellation are assigned names according to a historical system, and V838 Mon means that this was the 838th variable star designation in Monoceros. It is often shortened to V838 Mon, which is helpful because astronomers have enough long names to manage without using every available syllable before breakfast. During the first days of the eruption, it was also called Nova Monocerotis 2002. But that temporary label became increasingly uncomfortable as the source continued changing. Its light curve was especially strange. Instead of producing one clear maximum followed by a fairly orderly decline, V838 Mon passed through several major brightenings during the first months of 2002. The source rose quickly in January, reached another strong maximum in February, and then brightened again during March and April as its spectrum moved toward lower temperatures. The precise divisions between the peaks depend on the wavelength and measurements being considered, but the overall pattern was unmistakable. Something was releasing energy in stages. Either several episodes were occurring inside the source, or expanding layers were revealing different parts of the event at different times. Near its brightest visible stage, V838 Mon reached roughly magnitude 6.7, placing it near the limit of unaided human vision under a sufficiently dark sky. That number may not sound dramatic until it is compared with its earlier brightness, near magnitude 15.6. Because the astronomical magnitude scale is logarithmic, the change represented an increase of several thousand times in visible brightness. At its distance, the intrinsic luminosity was extraordinary, temporarily making it one of the brightest individual stars in the Milky Way. The energy did not remain concentrated in a hot compact surface. The apparent photosphere expanded, the temperature dropped, and the spectrum moved steadily through the classes associated with cool giant stars. Ordinary novae usually become optically thin after their eruption. As their ejecta spread out, astronomers begin seeing emission lines from increasingly exposed ionized gas. The central source can become very hot. V838 Mon followed almost the opposite route. Its atmosphere remained dense and cool. Absorption features from low ionization atoms were prominent. Broad Piscini profiles, which are produced when an expanding atmosphere absorbs light on the approaching side, while emitting across a wider velocity range, revealed substantial mass loss. Later, strong molecular bands appeared as the material reached temperatures low enough for molecules to survive. Instead of revealing a hot compact remnant, the source seemed to expand into an increasingly cool and enormous object. For a short period, its spectrum became cooler than the spectra of ordinary red supergiants. Researchers compared it with late M-type stars and even with L-type objects, a category normally associated with brown dwarfs, rather than stars possessing many times the Sun's mass. This was not because V838 Mon had suddenly become a brown dwarf. Spectral classes describe temperature and atmospheric features, not simply total mass. The extraordinary point was that a highly luminous merger remnant had developed an atmosphere cool enough to produce features normally seen in much fainter objects. It was, in effect, behaving like an impossibly enlarged version of a very cool star. Such rapid cooling supported the idea that a large amount of material had expanded outward. As the photosphere grew, the available energy was spread across a greater area. The gas used internal energy to perform the work of expansion and lost heat. The source became redder, while its enormous size allowed it to remain luminous. This was the same general evolution we have already followed, but V838 Mon provided one of the clearest real examples. The theoretical sequence of heating, expansion, recombination, molecule formation, and dust production was occurring in a particular system whose changing spectrum could be measured night after night. Early explanations ranged widely, because nothing quite like it had been studied with such detailed coverage. Some researchers considered an unusual thermonuclear event. Others examined the possibility of a late helium shell flash in an evolved star, similar in broad outline to the events sometimes called born-again stars. There were suggestions involving a massive star eruption, the engulfment of planets, or a collision between stars. Each model could explain one or two observations, but many had difficulty explaining the whole collection. The young stellar environment, the repeated maxima, the extraordinary expansion, the cooling remnant, the companion star, and the failure to develop the hot phase expected from some nuclear eruption models. The stellar merger explanation gradually became the strongest. In this picture, a star combined with a lower mass companion, releasing orbital and gravitational energy in several stages. Different episodes of the interaction could account for the repeated brightenings. The expanding shared envelope naturally produced the large, cool photosphere. The event left behind a swollen star instead of a destroyed one. Later discoveries, especially the clear pre-merger orbital record of V1309 Scorpii, strengthened the general connection between outbursts of this kind and merging binaries. Studies of V838 Mon's remnant now commonly describe it as the product of a luminous red nova merger, although the exact masses and evolutionary states of the stars that merged remain less directly established than in V1309 Scorpii. V838 Mon was not alone when the eruption occurred. Spectroscopy revealed a hot B-type companion whose light could still be detected beside the cool merger product. Later, high-resolution observations showed that the wider system was probably triple, or even more complicated, before the eruption. The merger involved members of a young stellar system, while another B-type star remained at a separation of roughly a few hundred astronomical units. That surviving companion did more than provide information about the system's age. Ejecta from the 2002 event eventually reached its surroundings, where the companion's radiation, gravity and wind began changing the flow and chemistry of the material. The central eruption alone would have made V838 Mon an important object, but another phenomenon turned it into one of the most widely recognized stellar images ever produced. Soon after the brightening, observers noticed light appearing around the star. In ground-based images, a surrounding glow seemed to expand. When the Hubble Space Telescope began observing the region with its advanced camera for surveys, the structure became astonishingly detailed. Rings, arcs, cavities, swirls and knots appeared around the central source. Images taken months apart showed the illuminated region growing and changing, as though an enormous nebula were rushing outward from the star. At first glance, it looked like the eruption had thrown out a vast shell that crossed several light years in only a short time. That interpretation would have required matter to travel faster than light, which would have caused a fairly serious disagreement with relativity. Fortunately, the dust was not moving outward at anything close to that speed. Most of it was already present around the star. The thing moving across the dust was the illumination produced by the 2002 flash. This is a light echo. The term is borrowed from sound because the basic timing resembles hearing a delayed reflection. When someone calls out near a distant wall, sound travelling directly to you arrives first. Sound that travels to the wall and then returns follows a longer route, so it arrives later. With a light echo, the direct flash from the star reaches Earth first. Other photons travel away from the direct line, strike dust grains, scatter, and then continue toward Earth. Their route is longer, so they arrive after the original outburst. The delay can range from days to years, depending on the location of the dust. The comparison with sound is useful, though the scale is very different. Light moves too quickly for an echo from an ordinary room to be noticeable. Space provides the required distances. If dust lies light months or light years from a star, the additional journey becomes long enough to produce visible delays. Each Hubble image of V838 Mon was therefore showing light from the 2002 eruption, reaching a different arrangement of dust, and then being redirected toward us. The flash had turned the surrounding interstellar material into a temporary three-dimensional screen. Suppose a dust cloud lies slightly in front of V838 Mon from our perspective. Light can travel from the star to that cloud, scatter toward Earth, and arrive only a little later than the direct flash. Dust farther to the side requires the photon to make a larger detour so its echo reaches us later. Dust behind the star can also contribute, but the route and scattering angle are different. At any given time after the eruption, the echo we see comes from dust lying on a particular curved surface defined by equal travel time. Because Earth is enormously distant compared with the size of the echo, this equal delay surface is usually described approximately as a paraboloid. The star lies near its focus, and the curved surface opens toward the observer. Where that moving paraboloid intersects sheets, filaments, or clumps of dust, a bright arc appears in an image. As more time passes, the paraboloid expands through space and intersects new material. A ring can grow, break apart, disappear, or be replaced by another structure, even though the dust itself has barely moved. This geometry explains the apparent faster-than-light expansion. The illuminated pattern is not one object travelling from the star to the outer edge. Widely separated dust regions are being reached by different photons emitted during the same outburst. The location of the visible intersection can sweep across a cloud faster than light, without carrying matter, energy, or information sideways at that speed. A similar effect occurs when the spot from a laser pointer sweeps across a distant surface. Move the pointer quickly enough, and the spot's position can cross the surface extremely fast, but no individual object is racing along the full path from one side to the other. In V838 Mon, the effect was particularly striking, because the dust distribution was complicated and the eruption was bright. Hubble resolved details that ground-based telescopes blurred together. Each new observation seemed to reveal a differently arranged nebula. Bright arcs appeared to push into dark regions. Thin filaments became visible and then faded. Cavities opened around the central source. The sequence looked almost alive, although what was truly changing was which dust happened to be receiving and scattering the delayed light at that moment. Colour added further information. Dust does not scatter every wavelength equally. Smaller grains tend to scatter shorter, bluer wavelengths more efficiently, while longer wavelengths pass through more easily. The scattered echo could therefore look bluer than the direct light from the cool remnant. Different sections also reflected light from different stages of the multi-peaked eruption. Because V838 Mon changed colour as it brightened and cooled, dust at one location could scatter the earlier hotter light, while another region returned light from a later redder maximum. The echo was not merely showing where the dust was. It was preserving delayed views of the changing outburst. In principle, this means that a light echo can allow astronomers to examine an eruption again from different directions. Dust placed around the source acts somewhat like a set of natural mirrors. Each cloud receives light that left the star along a different path. By studying the spectrum of the scattered light, researchers can learn how an explosion or eruption might have looked from another angle. This technique has even been used to investigate old supernovae whose direct light reached Earth centuries ago. VOR 838. MON offered a much more immediate laboratory because the original event had been observed directly, and the surrounding echo could be followed as it developed. The Hubble images also offered a way to measure distance. Light travels at a known speed, so the physical size of certain echo features can be connected with the time since the outburst. The difficulty is that the apparent angular expansion depends on the unknown three-dimensional position of the dust. A simple expanding ring does not automatically give a reliable distance, because the dust may lie in front of or behind the star. Early distance estimates based on oversimplified echo geometry turned out to be much too small. Polarization provided a more powerful method. When light scatters from dust at an angle near 90 degrees, it becomes strongly polarized, meaning its electric field has a preferred orientation. At a known time after the flash, dust scattering at roughly 90 degrees lies at a predictable physical distance from the star. Hubble's polarimetric images revealed a highly polarized ring. Comparing its angular radius with the physical radius implied by the light travel time allowed researchers to derive a geometric distance of about 6.1 kiloparsecs, with an uncertainty of roughly 0.6 kiloparsecs. That corresponds to around 20,000 light-years. This measurement placed V838 MON far beyond the distance initially inferred from simpler models, and confirmed that the eruption had been extremely luminous. The light echo was therefore not only a striking image, it was a measuring instrument created by the eruption itself. The star produced the flash, the dust scattered it, and the known speed of light supplied the ruler. Astronomers merely had to work out the geometry, which is the sort of sentence that makes a complicated calculation sound suspiciously like assembling a flat-packed wardrobe. The dust revealed by the echo also raised questions about the system's past. Early interpretations suggested that the illuminated material might have been expelled during previous episodes of mass loss from V838 MON. Some of the Hubble structures seemed roughly centered on the star, encouraging the idea of old circumstellar shells. Later analyses examined the three-dimensional distribution and total mass of the echoing material more carefully. Much of it appears to be interstellar dust, probably related to the cloud in which V838 MON and nearby young stars formed, rather than matter produced entirely by earlier eruptions of the same star. The distribution lacks the simple spherical symmetry expected from a series of ordinary stellar winds, and estimates of the mass make a purely stellar origin difficult. That does not mean every grain around the system is unrelated to V838 MON. The merger certainly expelled its own material, and later observations have detected dust and molecules close to the remnant. The large-scale light echo, however, illuminated a much wider environment. It mapped dusty material extending across several light-years, far beyond the ejector's possible travel distance since 2002. The echo was revealing both the immediate history of the eruption and the much older structure of the star-forming region around it. The distinction between the echo and the actual ejector is important. In the famous Hubble images, the large surrounding patterns are mostly scattered light moving across pre-existing dust. Much closer to the central star lies real material expelled by the merger. That matter travels at hundreds of kilometers per second rather than at the speed of light. It is warm, molecular, dusty, and dynamically connected to the remnant. Telescopes operating at infrared and radio wavelengths can study this nearer material even after the visible echo has become faint. Years after the eruption, interferometric observations showed that the central object remained extremely large. Its apparent photosphere gradually contracted, indicating that the swollen merger product was releasing energy and moving slowly toward a more stable state. Dust was distributed across hundreds of astronomical units, with evidence for a flattened or elongated structure. The geometry suggested that the old orbital plane continued influencing the material long after the two merging stars had lost their separate identities. ALMA later mapped molecular gas and dust around the system at high angular resolution. These observations revealed a clumpy wind around the cool merger remnant, an elongated central feature interpreted as a possible disk, and a complicated region where the 2002 outflow interacts with the surviving B-type companion. Molecules including carbon monoxide, silicon monoxide, sulfur monoxide, sulfur dioxide, aluminium hydroxide and hydrogen sulfide were detected in the surrounding gas. This chemistry provided a very different view from the optical light echo. Hubble mapped the distant dust through reflected light, while ALMA studied the cold material produced and disturbed by the merger itself. More recent high-resolution infrared work has found evidence for asymmetric and bipolar structures close to the remnant. Such shapes are consistent with the expectation that a merger ejects matter unevenly, often placing dense material near the old orbital plane while allowing outflows to move more freely in other directions. The exact structure remains under investigation, but V838 Mon is clearly not surrounded by one simple spherical shell. The system contains layers and components created at different times, from the large interstellar cloud illuminated by the echo to the much smaller dusty structures shaped by the merger. The surviving B-type companion adds another moving part. As merger ejecta expanded outward, some of it passed across the companion's line of sight or entered the companion's environment. Researchers observed changes in spectral emission and an eclipse-like event that were interpreted as interactions between the expanding material and the hot star. Its ultraviolet radiation ionized parts of the otherwise cool flow. Gas may also have been accreted onto the companion, creating shocks near its surface. A star that had not taken part in the central merger was still being affected years later by matter launched during it. All of this makes V838 Mon a remarkably layered event. At the smallest relevant scale is the unresolved merger product still rotating and contracting. Around it lies newly formed dust, molecular gas, possible disk-like material, and asymmetric outflows. Farther away is the surviving stellar companion interacting with the expanding ejecta. Beyond that lies the larger interstellar cloud whose filaments were illuminated by the flash. Finally, after travelling roughly 20,000 years from the system to Earth, the direct and scattered light reached our telescopes during the first years of the 21st century. The timing can feel slightly strange. The merger did not physically occur in 2002 at V838 Mind. It occurred around 20,000 years earlier, because that is approximately how long its light took to reach us. We describe 2002 as the year of the eruption, because that is when Earth received the signal. By the time the first observer noticed the brightening, the remnant itself had already spent thousands of years continuing its evolution. Astronomy allows us to watch distant events, but it never allows us to watch them live in the ordinary sense. Every view is delayed, and a light echo adds further delays inside the delayed view. The Hubble sequence therefore showed us echoes of an outburst that was already ancient when its direct light arrived. The central flash reached Earth first. Scattered photons followed months and years later because they had taken longer routes through the dusty environment. Each image was a later delivery of light emitted during the same short period. There was no new eruption required for every expanding ring. The universe was simply sending the original message by several paths, apparently having decided that ordinary postal efficiency would make the geometry less interesting. V838. Mon also changed the way astronomers regarded earlier unusual red transients. Before 2002, events such as M31-RV in the Andromeda Galaxy and V4332 Sagittarii in the Milky Way had already shown some similar behaviour. They brightened and evolved toward a cool red spectra, but their nature was uncertain. V838 Mon was close and bright enough to receive exceptional attention across the electromagnetic spectrum. Its repeated peaks, cool expansion, dusty remnant and famous echo encouraged researchers to recognise a broader family of stellar eruptions, rather than treating each case as a completely unrelated oddity. Even then, the connection to mergers was not immediately proven. A model can explain a collection of evidence and still lack the one observation everyone would most like to possess: a direct record of two stars approaching each other before the outburst. V838. Mon's pre-eruption system was too distant and insufficiently monitored to provide a clear shrinking orbital signal. Its merger interpretation was built from the outburst, the remnant, the stellar environment, and comparisons with other events. What V838 Mon gave astronomy was a prototype. It demonstrated how luminous, cool, and complicated a non-terminal stellar outburst could become. It showed that a star could expand dramatically without undergoing a supernova. It produced molecular and dusty conditions rarely seen so soon after a bright eruption. Its light echo turned surrounding interstellar dust into a three-dimensional map, gave researchers a geometric distance, and supplied Hubble with a sequence of images that made a difficult stellar process visible to almost anyone. Yet a prototype is not always the clearest proof of a mechanism. V838. Mon showed astronomers what the aftermath of a likely merger could look like, but another object would reveal the approach far more directly. V1309, Scorpii did not first become important because it produced the brightest red nova ever recorded, the largest light echo, or the most spectacular image. Its great value came from something much quieter. For years before the outburst, the system had been measured repeatedly without anyone realizing that two stars were approaching the end of their shared orbit. Those observations remained stored in an archive, preserving the changing rhythm of the binary until the eruption made researchers return and examine what had been happening beforehand. When they did, they found the evidence astronomers had long hoped to see: a contact binary whose orbital period was shrinking as the two stars moved toward a merger. The object lies in the constellation Scorpius, in a crowded region of the Milky Way where many stars overlap along our line of sight. It was discovered as a new transient on September 2nd, 2008, when it had reached an apparent brightness of approximately magnitude 9.5. At first, it was announced as a possible classical nova. That classification was understandable. A previously faint source had brightened rapidly, and the sky does not provide a small label beside each eruption explaining the machinery responsible. The object became known as Nova Scorpii 2008, and later received its variable star name, V1309 Scorpius, usually shortened to V1309 SCO. It did not attract the same immediate attention that V838. Monocerotis had received several years earlier. V1309. SCO was relatively faint, positioned in a crowded field, and lacked a vast light echo waiting to turn its surroundings into a Hubble display. Much of the available photometry during the eruption came from amateur observers, rather than from a coordinated campaign involving the largest observatories. Spectroscopy, however, soon showed that the event was not behaving like a classical nova. Instead of evolving toward the hot, ionized state expected after a thermonuclear eruption on a white dwarf, it developed progressively cooler spectral characteristics and eventually resembled a late M-type giant. That cooling connected it with V838 Mon and other unusual red transients. Gas around V1309, SCO expanded at relatively modest stellar ejector speeds, molecular features became important, and dust developed as the source faded. The event had the appearance of a luminous red nova, but appearance alone did not prove that the cause was a merger. Before V1309 SCO, stellar coalescence was already considered a strong explanation for objects such as V838MON. The difficulty was that astronomers usually encountered these systems after the decisive interaction had occurred. They saw the brightening, the cooling atmosphere, and the dusty remnant, then tried to infer whether two stars had once been present. Voisiwan 309 SCO was different because its position happened to fall within an area monitored by the Optical Gravitational Lensing Experiment, or OGLE. OGLE was not created specifically to wait for stellar mergers. Its principal goals included finding gravitational microlensing events and studying variable stars by repeatedly imaging dense stellar fields. That required careful brightness measurements taken over many years. Beginning in August 2001, the project recorded Phi-1309 SCO's progenitor again and again, producing a long photometric history before the 2008 outburst. At the time, the source was one variable point among an enormous number of stars. Nothing in the early data announced that it would soon become one of the clearest merger examples in astronomy. Its brightness rose and fell regularly with a period near 1.4 days. Such repetition strongly suggested an eclipsing or tidally distorted binary. Every orbit presented the stars from a changing angle. At some phases, one component moved partly in front of the other. At other phases, the elongated sides of the stars offered a large combined area toward Earth. The result was a repeating light curve that encoded the geometry of the system. The roughly 1.4-day period meant that the two stars were extraordinarily close by ordinary stellar standards. Earth takes 1 year to orbit the Sun. Mercury completes its orbit in 88 days. These two stars circled their common centre in a little more than 1 Earth day. Their surfaces were not separated by the comfortable distances found between planets. They formed a contact binary, meaning that both stars filled their Roche lobes and shared outer material. From a distance, the system would have looked less like two separate spheres and more like one rotating peanut-shaped envelope containing two inner stellar centres. Early in the OGLE record, the brightness pattern displayed the familiar features of a contact binary. There were 2 maxima and 2 minima during each full orbital cycle. One minimum could occur when one star passed in front of the other, while the second appeared half an orbit later when their positions were reversed. The maxima occurred when the elongated sides of the contact system were displayed more fully. The 2 dips did not have to be identical because the stars could differ in temperature, size, surface structure, and brightness. If the system had remained stable, each cycle would have repeated at almost the same interval. Instead, careful analysis showed that the period was decreasing. The change was too small to notice by simply watching a few nights of data, but over years, the accumulated difference became unmistakable. A maximum expected at one time arrived slightly early. The next arrived earlier still. The orbital clock was gaining time because the stars were completing their circuits more quickly. Between the early observations and 2007, the measured period fell from around 1.44 days toward roughly 1.42 days. A change of a few hundredths of a day may appear minor. It is only tens of minutes across several years. Yet orbital period and separation are closely linked. A shorter period indicates that the stellar centres are moving around a smaller orbit, assuming their masses are not changing in some perfectly compensating way. The 2 stars were spiralling inward, and the rate of change itself was accelerating. Researchers often describe the decline as approximately exponential during the observed years. The period decay timescale, calculated by comparing the period with the rate at which it was changing, shortened from roughly 1,000 years to around 170 years in less than 6 years. This did not mean the system had exactly 170 years left. The shortening timescale showed that the evolution was accelerating so strongly that a simple, steady prediction was no longer appropriate. The binary was approaching an instability rather than continuing along a slow, uniform path. A useful comparison is a ball rolling down a slope that becomes steeper as it descends. Measuring its early movement might suggest a long journey, but the speed keeps increasing. Near the bottom, a forecast based on the original pace becomes meaningless. V1309 SCO's orbit behaved in a similar way. Each stage of shrinkage altered the mass transfer, rotation, and gas flow, which then encouraged further shrinkage. The stars were not following a clock that could simply be extended forward with a ruler. The shape of the light curve changed as well. From 2002 through 2006, 2 maxima and 2 minima remained visible, but the relative heights and depths evolved. One maximum gradually weakened. The waveform became increasingly unequal, and less like the stable, repeating pattern expected from a settled contact binary. During 2007, the changes became more pronounced, and the second maximum eventually became difficult to identify. The orbit was still influencing the brightness, but the visible system was becoming more complicated than 2 exposed stellar surfaces moving around one another. One explanation is that gas leaving the binary was beginning to obscure parts of the orbit. As the mass loss rate increased, the stars could become surrounded by an optically thick outflow. The repeating signal would then be viewed through an expanding layer of material whose brightness and opacity were changing. Instead of seeing the surfaces directly at every phase, observers saw a growing photosphere formed within gas leaving the system. The orbit continued inside, but its clean pattern was being buried. The changing light curve may also have reflected differences between the orbital motion and the rotation of the shared envelope. If the outer material could no longer remain synchronized with the increasingly rapid orbit, friction and shear would heat particular regions. The brightness might then depend on which side of the system faced Earth, producing a stronger maximum during one part of the cycle than during the other. Several physical effects may have operated together. The essential observation was that the binary's visible geometry and period were both changing as the merger approached. Why was the period shrinking? The stars had to lose orbital angular momentum. Gas flowing out through the outer Lagrange point could carry a large amount away because it left from a region far from the system's centre of mass. Material did not need to escape as one spherical wind. Rotation naturally guided it into a broad equatorial stream or spiral. As the gas departed, the orbit lost some of the angular momentum that had kept the 2 stellar centres apart. The separation decreased, causing stronger interaction and more mass loss. The process could become self-reinforcing. A slight increase in mass loss removed more angular momentum. Losing angular momentum shortened the orbit. A shorter orbit pushed the shared stellar envelope further out of equilibrium and increased the transfer or escape of gas. That additional gas then removed still more angular momentum. The binary had entered a feedback loop in which the usual mechanisms preserving a stable contact configuration could no longer keep up. Some models connect the final instability with the enormous difference in mass between the 2 stars. Hydrodynamic studies have explored a system containing a giant of roughly 1.5 solar masses and a much smaller companion of around a few tenths of a solar mass, though the precise progenitor properties are model-dependent rather than directly measured with perfect certainty. In these calculations, the binary can become Darwin unstable, meaning the orbit does not contain enough angular momentum to keep the extended stellar envelope synchronized. The companion then plunges inward, while matter escaping through the outer Lagrange region forms ring-like ejecta. The smaller companion was not simply falling onto a passive larger star. Both objects had already been altered by a long history of mass exchange. Evolutionary models suggest that the system may have begun with 2 stars of unequal mass in a wider orbit. The originally more massive star evolved first, expanded and transferred material to its companion. That exchange could reverse the mass ratio, leaving the former donor as the lower mass component while the receiver became the dominant star. Later expansion and continued angular momentum loss brought them into deep contact and eventually toward coalescence. By 2007, evidence suggests that the binary was already losing dusty material. Infrared data indicate the presence of warm dust at a temperature of roughly 900 to 1000 Kelvin before the main outburst. Dust that warm must have been comparatively close to the system and probably newly formed within material expelled by the spiraling binary. The stars were preparing the environment into which the later eruption would expand. This detail is important because the bright red nova did not begin in empty space. Before the final merger, gas had already accumulated around the orbital plane. Some of it cooled enough to form dust. When faster ejecta were launched during the dynamical event, they encountered this older material. Shocks, absorption, and reprocessing within the surrounding gas shaped the later light curve. The months-long rise was not merely the surface of one star becoming brighter, it was the entire outflow becoming larger, thicker, and more luminous as the mass loss rate increased. In March 2008, roughly half a year before the transient was officially discovered, V1309 SCO began a systematic brightening. The change marked the beginning of the violent merger phase in the OGLE interpretation. The binary had not yet reached its September maximum, but the system was no longer behaving like the earlier contact star. Its mean brightness increased, the regular orbital modulation became difficult to trace, and the growing outflow increasingly concealed the original components. The slow rise lasted for approximately 200 days. One model explained it through continuous accelerating mass loss from the binary. Gas escaping through the outer Lagrange region formed an optically thick wind or outflow around the system. As the mass loss rate rose, the radius of the effective photosphere expanded. A larger photosphere radiated more light, so the source brightened gradually even before the most dynamic stage of coalescence. The binary was, in a very literal astronomical sense, burying itself inside its own escaping material. From Earth, that burial removed one of the most valuable clues. The neat periodic signal faded because the stars were no longer directly visible through every orbit. Yet its disappearance was itself informative. A stable binary would have continued producing a repeating pattern. V1309 SCO's periodicity weakened as the system brightened, then did not return after the eruption. The orbital clock stopped because there was no longer a stable exposed pair producing it. The final plunge probably released material in several episodes. Simulations suggest that mass loss through the outer Lagrange point may have occurred during the days immediately before merger, creating an equatorial ring or torus. The companion then sank into the primary envelope and transferred orbital energy into surrounding gas. Additional ejecta carried away a significant fraction of the system's angular momentum, even if the total amount of expelled mass represented only a small fraction of the stars. Removing a little material from the outer parts can be very effective, because that material carries more angular momentum per unit mass than gas near the centre. As the stellar interiors combined, the source brightened by many magnitudes. The visible outburst reached its maximum in September 2008, and then remained near a broad plateau for several weeks before declining. Estimates suggest that it radiated roughly a few times 10 to the 44 ergs during the plateau-like maximum. That is far below the energy of a typical supernova, but enormous compared with ordinary stellar variability. The event occupied the range expected for a low-luminosity red nova, created by relatively modest mass stars. Spectra taken during and after the outburst showed a complicated environment rather than one simple spherical shell. Narrow absorption features trace slower, circumbinary material that had probably been produced before the main eruption. Broader emission came from faster matter expelled during the merger. Later analyses have interpreted the 2008 ejecta as a dusty bipolar flow, while the older surrounding gas occupied a more torus-like arrangement around the former orbital plane. The geometry preserved a memory of the binary even after the stars had become one. The source also became progressively cooler as it faded. Its spectral appearance evolved from something resembling an F-type giant toward a late M-type giant, following the pattern that connects red novae with expanding, cooling merger ejecta, rather than classical nova explosions. Molecules appeared, dust formed efficiently, visible light declined as the central remnant became enclosed within material that absorbed shorter wavelengths and re-radiated the energy in the infrared. Shortly after the eruption, V1309 SCO was almost completely embedded in dust. By 2010 and 2012, infrared observations showed an extended dusty envelope containing material lost during the 2008 event. Estimates placed at least 1,000th of a solar mass in that envelope, although the true amount could be larger. The source remained intrinsically luminous even while it became extremely faint in visible light. By 2012, its total luminosity had fallen by a factor of roughly 50 from maximum, but the decline was far less complete than optical photographs alone suggested. This is another reason V1309 SCO became so useful. Astronomers could compare 3 distinct stages of one merger. The pre-outburst observations showed a contact binary losing orbital period. The slow rise showed the system enveloping itself in an accelerating outflow. The eruption displayed the release of energy and mass during coalescence. Later infrared observations revealed the dusty remnant after the regular binary signal had disappeared. No earlier red nova offered that full sequence so clearly. V838 Mon showed a far more famous aftermath, but its original binary orbit had not been recorded contracting toward merger. V1309 SCO was less dramatic visually, yet far more direct dynamically. It showed that the merger hypothesis was not merely one explanation among several that happened to reproduce a cool red outburst. A binary had been observed before the event. Its period had shortened. Its light curve had changed. It had begun losing material. It had brightened into a red nova. Afterward, the orbital pattern was gone. Researchers sometimes call V1309S CO a Rosetta Stone for luminous red novae. The comparison is appropriate because one well-recorded event helped translate the behaviour of many others. V838 Monocerotis, V4332 Sagittari M31-RV, and related transients could now be interpreted with greater confidence as products of stellar mergers or severe common envelope interactions. Their cool expansion, multi-peaked light curves, dust formation, and surviving central objects were no longer separate oddities. V1309 SCO connected them through a directly observed progenitor. It also encouraged astronomers to search for future mergers before they occur. Repeated surveys can measure the orbital periods of contact binaries and look for systems whose cycles are shortening. In theory, an accelerating period decline similar to that of V1309 SCO could provide warning that another merger is approaching. In practice, the task is difficult. Contact binaries can show period changes for many reasons, including magnetic activity, mass transfer, star spots, or the influence of an unseen third star. A short period alone does not mean that an eruption is about to occur. Even a rapidly changing period may not allow a reliable date. V1309 SCDO's decline accelerated toward merger, but fitting one mathematical curve to a limited interval can produce a forecast that shifts whenever new data arrive. The underlying physics can change as the stars move from contact into mass loss, common envelope evolution, and dynamical plunge. A prediction based on the early stage may fail once a new mechanism takes control. Astronomy would prefer a tidy countdown. The stars have declined to install one. Still, V1309 SCO offers several possible warning signs. The orbital period shortened increasingly quickly. The light curve shape evolved. The system brightened gradually before the main event. Infrared observations suggest that fresh dust formed in pre-merger mass loss. The periodic signal then disappeared as an optically thick outflow buried the binary. A future system displaying the same collection of changes would deserve extremely close attention. Catching such an object in advance would allow telescopes to record the transition with much better coverage than was possible in 2008. Spectra could measure the earliest escaping gas. Infrared instruments could watch dust condense before the outburst. Radio telescopes could trace molecules. polarization could reveal the changing geometry. Space observatories could follow the rise without interruption by daylight or weather. Researchers could test whether the outflow first forms around the equator, how quickly the stellar orbit vanishes from view, and when the fastest merger ejecta are launched. Gravitational waves from ordinary stellar mergers would be far weaker and lower in frequency than the signals detected from compact black hole or neutron star mergers, making them very difficult to measure with current instruments. For the foreseeable future, light remains our main messenger from systems such as V1309 SCO. Fortunately, its light carries several forms of information at once. Regular brightness variations reveal the orbit, colour measures temperature, spectral lines reveal speed and composition, infrared emission reveals dust. The disappearance of periodicity tells us that the former binary structure no longer presents itself as two orbiting stars. The absence of the old orbital rhythm does not mean that the remnant has become simple. The merged object is expected to rotate rapidly because it retains part of the former orbit's angular momentum. Its interior has been heated and mixed. It may rotate at different rates at different depths. Material can fall back from the ejecta, and a disk or torus may remain around it. Dust hides the central star while molecules and atoms scatter whatever radiation escapes through clearer directions. Years after the event, V1309 SCO remained faint in visible light, but bright at infrared wavelengths. Its spectrum became dominated by emission from neutral atoms and molecules within circumstellar material. The central remnant was not directly visible along every line of sight, but its radiation continued illuminating the gas around it. The system had not vanished. It had changed into an object that required different instruments and different wavelengths to study. That transformation contains the final lesson of the pre-merger observations. Before 2008, V1309 SCO was easy to describe in familiar terms, a contact binary with a period close to 1.4 days. During the final approach, that description became steadily less adequate. Gas loss created a surrounding photosphere. The periodic light curve changed and disappeared. The two components merged. Afterward, the central source remained hidden within ejecta that carried away mass, energy and angular momentum. The ordinary-looking point monitored by OGLE had therefore preserved an entire transition between stellar categories. It began as two stars in a shared envelope, became a bright red transient, and then settled into a single dusty remnant. The system demonstrated that the visible fading of a red nova does not mark the disappearance of its energy or the end of its evolution. It marks the point at which the most obvious light leaves our instruments, while the merged star continues adjusting behind the material it expelled. The bright eruption may have passed, but the red nova has not truly ended. Visible light is only one part of the event, and it is often the first part to become difficult to detect. Dust thickens around the central obdrum ordinary optical telescopes. To someone watching only through visible wavelengths, it can seem as though the source has simply faded back into the crowded background of the galaxy. Infrared instruments tell a different story. They continue detecting heat from dust, molecules, and a swollen survivor whose structure has not yet settled. Long-term observations of several luminous red novae show that their remnants can remain bright in the near and mid-infrared for years, even after becoming fainter in visible light than the systems that existed before the merger. Is no longer the original binary. The repeating orbital signal has disappeared because two separate stars are no longer presenting their surfaces to us in a predictable cycle. In their place is a merged object containing most of the mass that once belonged to the pair, minus whatever material escaped during the common envelope phase and final coalescence. Calling it one star is correct in the broad sense, but it can give an impression of order that has not yet been achieved. The remnant is likely to be enlarged, rapidly rotating, internally mixed, and surrounded by gas whose motion still reflects the former orbit. The new star has more energy than an ordinary star of the same mass an evolutionary stage would normally contain in its outer layers. Friction, shocks, compression, and the collision of stellar material have deposited heat throughout the remnant. That heat causes the envelope to expand. A larger stellar envelope has a lower surface temperature than a compact one with a similar luminosity, so the survivor may resemble a very cool giant or supergiant. It can remain hundreds of times wider than the Sun while slowly radiating the energy introduced by the merger. This swollen state cannot continue unchanged forever. Gravity pulls inward, while pressure and rotation provide support. As energy escapes, the remnant can gradually contract. Contraction converts additional gravitational energy into heat, delaying the process. The adjustment, therefore, does not happen in a few evenings. Depending on the mass, internal structure, amount of retained heat, and strength of continuing mass loss, the remnant may require years, decades, centuries, or longer to approach a more ordinary equilibrium. During that interval, its apparent size and temperature can change substantially. A shrinking remnant may grow hotter at the surface because the same or slowly changing luminosity is emerging through a smaller area. On the other hand, continued dust formation can conceal that rise from visible observations. Infrared measurements, spectroscopy, and high-resolution interferometry are needed to separate the actual stellar surface from the warm material around it. What appears as one cool source may contain a hotter inner object, a molecular atmosphere, several dust temperatures, and ejecta distributed across very different distances. V838 Monocerotis provides a useful example. Years after its 2002 eruption, observations continue to show a very large, cool central object surrounded by dust and molecular gas. High-resolution measurements found asymmetric structures rather than a single simple shell. A possible disk-like component, clumpy outflows, and interactions with the surviving wider companion all showed that the merger's surroundings remained active long after the famous optical light echo had begun fading. The remnant was not calmly returning to normal. It was still redistributing matter and energy through a complicated stellar environment. Followed the same broad rule in a less visually famous way. After the binary merged in 2008, the source became deeply hidden by dust. Its visible brightness fell dramatically, yet infrared observations continue to reveal a luminous object. The original contact binary, with its 1.4-day period, was gone. What remained was a cool merger product surrounded by material created during the final years of orbital decline and the eruption itself. Dust is one of the most persistent parts of the aftermath. Some grains form before the final merger within gas lost from the shrinking binary, more condensed later as expanding ejecta cool. These grains absorb visible and ultraviolet light from the central remnant, warm up and re-radiate the energy in the infrared. As the ejecta continue outward, the dust temperature usually falls. Hot dust close to the star may glow in the near-infrared, while cooler grains farther away emit mainly at longer wavelengths. The dust does not necessarily form a uniform sphere. The old orbital motion encourages material to gather near the equatorial plane, producing a torus, thick disk or flattened flow. Faster ejecta may escape more easily toward the poles, creating a bipolar structure. Clumps form where gas cools unevenly, or where shocks compress particular regions. An observer looking through the dense equatorial material may see a heavily obscured remnant, while someone viewing the same system from another direction might see deeper and measure a hotter source. This geometry can survive for a very long time. Once the gas has expanded far enough, it is no longer easily rearranged by the central star. The shape becomes a record of the merger's final motion. A torus indicates where the orbital plane once lay. Bipolar lobes show where outflow encountered less resistance. Spiral patterns may preserve repeated episodes of mass loss before the stars fully combined. Even after the binary orbit is gone, the surrounding nebula continues displaying its former orientation. Not all the expelled gas escapes permanently. Some material receives enough speed to leave the system and eventually mix with the interstellar medium. Other material is pushed outward but remains gravitationally bound. it can slow, reach a maximum distance, and fall back toward the remnant. Studies of several red nova remnants suggest that fallback may continue years or even decades after the eruption, feeding the central object and altering the surrounding molecular environment. Material does not usually land in a straight line. It carries angular momentum inherited from the former orbit, so it can settle into a disk or rotating torus around the star. Collisions within this structure convert motion into heat. Material may accrete onto the remnant in irregular episodes, producing changes in brightness or driving additional winds. If magnetic fields are strong, they may guide some of the gas and help launch collimated outflows. The central remnant itself is expected to rotate rapidly. Before the merger, much of the system's angular momentum belonged to the orbit. Some left with the ejector, but a substantial fraction remained. Once two stars became one object, that angular momentum was stored mainly in rotation. The outer layers may spin fast enough to become flattened, and the equator may lose additional gas if centrifugal effects reduce gravity's hold there. Rotation is unlikely to be uniform throughout the star. The inner layers, newly deposited material, and outer envelope may turn at different rates. This differential rotation can drive turbulence and mix chemical elements between regions that would normally remain separate. It can also stretch and amplify magnetic fields. The remnant may therefore become far more magnetically active than either original star was before the merger. Stronger magnetic activity could produce large star spots, flares, winds, and irregular changes in brightness. It can also help transfer angular momentum from rapidly rotating inner regions to the envelope. Magnetized winds then carry some of that angular momentum into space, gradually slowing the star. This process is expected to take much longer than the bright red nova eruption, so the survivor may remain a rapid rotator well after its surrounding dust has cooled. Chemical mixing creates another lasting signature. Before the merger, each star contained layers with different compositions. Hydrogen dominated the outer regions, while deeper layers had been altered by nuclear fusion. The interaction can strip, stir, and combine parts of those layers. Material that had been buried may reach the surface, and fresh hydrogen may move into hotter regions. The final surface chemistry may therefore differ from that of an ordinary isolated star with the same mass and age. The degree of mixing depends strongly on the stars involved. A merger between two main sequence stars will not produce the same internal structure as a merger between an evolved giant and a smaller companion. If one star contains a dense helium core, that core may survive near the center while the companion's material spreads around it. If the two stars are more similar, their inner regions may mix more thoroughly. In either case, the remnant carries information about both original objects, but that information is rearranged rather than neatly stacked. Some merger products can appear younger than their surroundings. In a star cluster, most stars of a given mass should evolve on similar timescales. Yet blue stragglers sit above the expected main sequence turnoff, appearing hotter and more massive than the cluster age would normally allow. Many are thought to form through mass transfer or stellar mergers. A merger can combine the mass of two older stars and mix additional hydrogen into regions where it can support further fusion, producing an object that seems to have been given extra time. A red nova gives astronomers the rare opportunity to watch the transition into such a product, rather than discovering only the final unusual star. Not every red nova remnant will become a classic blue straggler. Some are too evolved, too dusty, or too massive, and their later paths differ. The general lesson remains that stellar age cannot always be inferred from appearance alone when binary interaction has rewritten the internal structure. Massive merger remnants may face particularly complicated futures. Combining two stars can create a single object with a mass, spin rate, and chemical profile unlike those of a star formed normally from one collapsing cloud. If the remnant is massive enough, it may eventually undergo core collapse and produce a supernova. Its rapid rotation and altered mass loss could influence the kind of explosion that occurs, though predicting that future requires knowing how much angular momentum survives and how the star evolves after the merger. The red nova itself is not that supernova. It does not normally destroy the central stellar core, yet it can change the conditions under which a later stellar death happens. The merger may increase the total mass, strip or preserve different layers, strengthen magnetic fields, and change the rate at which the star loses material. By the time the remnant reaches the end of nuclear burning, it may be very different from either of the stars that began the interaction. Lower mass remnants have quieter futures. They may contract into rapidly rotating main sequence or giant-like stars, and then continue evolving over millions or billions of years. Their ejecta disperse, their dust cools, and the event becomes harder to recognize. Unless some unusual chemistry, rotation, magnetic field, or surrounding nebula remains, a very old merger product may eventually look almost ordinary. The violence of its formation can be hidden beneath a stable stellar surface. The expelled material also contributes to the galaxy around it. Red novae do not synthesize enormous quantities of heavy elements in the way supernovae and neutron star mergers can. Their gas largely consists of material already present in the original stars. Even so, they return processed matter and dust to interstellar space. Molecules form within the cooling ejecta, grains grow, and the expanding remnant enriches the surrounding environment with material from stellar interiors. The chemistry can become surprisingly complex. Observations of nearby remnants reveal carbon monoxide, silicon monoxide, sulfur-bearing molecules, aluminium compounds, water-related species, and dust grains of several compositions. Shocks create temporary high-temperature reactions, while dense cooling regions allow molecules to assemble afterward. Studying these environments helps researchers understand how chemistry proceeds in rapidly changing stellar outflows. The molecular gas can also reveal movement that visible images cannot. Radio and millimeter observations measure spectral lines, whose Doppler shifts show which parts of the remnant are approaching and which are receding. From those velocities, astronomers reconstruct disks, lobes, clumps, and expanding shells. The central source may be completely hidden by dust, yet its surroundings continue describing what happened through the motion of molecules. Over longer timescales, the ejecta expand and become less dense. Dust temperatures fall. Shocks weaken as the gas loses speed and encounters the surrounding interstellar medium. Some molecules are broken apart by ultraviolet radiation. The remnant's nebula becomes larger, fainter, and increasingly difficult to distinguish from unrelated clouds along the same line of sight. Eventually, much of it disperses into the galaxy. Before that disappearance, the remnant can resemble other classes of evolved objects. Bipolar nebulae, dusty disks, and molecule-rich outflows are also seen around post-asymptotic, giant branch stars and objects developing toward planetary nebulae. Researchers have suggested that some sources classified as ordinary late stages of single-star evolution may actually be old merger remnants. If so, red novae could help explain a hidden population of strangely shaped nebulae whose central histories are not obvious from present-day observations. Remnants is difficult because time removes the clearest evidence. The bright eruption may have gone unrecorded. The original binary no longer exists. Dust and gas can imitate material produced through other kinds of stellar mass loss. Astronomers must look for combinations of clues: unusually rapid stellar rotation, odd surface chemistry, excess infrared emission, bipolar ejecta, a missing companion, or an age that does not match neighbouring stars. Historical transients may provide additional examples. Old records sometimes describe a new star that brightened and faded centuries ago. Modern telescopes can then search the location for cool molecular remnants. CK Vulpeculae, associated with an event seen in 1670, contains a highly unusual molecule-rich nebula and is often discussed as a possible merger remnant, although its exact nature remains debated. Such systems remind us that classification can remain difficult even when both the historical eruption and present-day debris are available. The remnant's uncertainty is not a failure of the red nova explanation. It reflects the diversity of the stars that can merge. A low-mass contact binary, a giant with a small companion, and two massive young stars do not create identical survivors. The amount of ejected mass, internal mixing, dust, rotation and fallback changes from one event to another. Red novae describe a family connected by severe binary interaction, rather than a production line making one standard object. What remains after the fading, then, is not merely a single star. There is a central merger product carrying heat and angular momentum from the former orbit. There is expelled gas, some escaping and some possibly returning. There are molecules and dust grains that shift the system's energy into the infrared. There may be disks, tori, bipolar lobes, magnetic activity, and a surviving wider companion. Each component preserves a different part of the interaction. The visible eruption lasted only a short time because the brightest radiation found its way out quickly. The physical consequences last much longer. The remnant must contract, cool or reheat, slow its rotation, rearrange its interior, and interact with the material around it. Its future can extend from a relatively ordinary stellar life to a later supernova, depending on the mass and evolutionary state of the system. That is why astronomers continue returning to red novae after they have faded. The early light curve reveals how energy escaped. The late infrared source reveals how much energy remained. Molecular observations trace cooling chemistry. High-resolution images reveal the geometry inherited from the orbit. Measurements of the central star show how a stellar body responds after two separate structures have been forced into one. As the dust continues moving outward, the old binary becomes less visible but not less important. Its orbit has vanished as a repeating signal, yet the consequences of that orbit remain in nearly everything we can still measure. The flattened ejector remember the orbital plane. The rotation of the survivor remembers the orbital angular momentum. The mixed composition remembers both stars. The infrared glow remembers the heat released during coalescence. By reading those traces, astronomers can move beyond the story of one unusual transient and use red novae to understand the much larger population of binary stars whose private interactions shape the galaxy. Most stars are not completely alone. A large fraction are born in pairs or in more complicated multiple systems, and among massive stars, close companionship is especially common. This means that the familiar picture of a star evolving entirely according to its original mass is incomplete. A companion can remove material, donate material, change an orbit, spin a star faster, expose inner layers, or merge with it. Red novae reveal the most direct and dramatic version of this influence, but their importance extends far beyond the few weeks when they brighten. An isolated star follows a comparatively understandable sequence. Its initial mass largely determines how quickly it burns fuel, how much it expands, what elements it produces, and how it eventually ends. A binary star has the same internal physics, but gravity connects its evolution to another changing object. The first star to expand may fill its Roche lobe and begin transferring gas. That transfer changes both masses. The orbit responds. The receiving star grows and spins up. Material can escape from the system and carry angular momentum away. From that point forward, neither star follows the path it would have taken alone. Red novae show us what happens when this interaction becomes unstable. Instead of settling into long-term mass transfer, the system develops runaway overflow, deep contact, a common envelope, and sometimes a complete merger. The outburst turns a normally hidden process into something observable. Brightness, colour, spectral lines, infrared emission, and pre-eruption measurements allow researchers to test ideas that would otherwise remain inside computer simulations. Current reviews describe red novae as some of the clearest direct observational probes of unstable mass transfer, binary coalescence, and common envelope evolution. The common envelope phase is important because it can produce two opposite outcomes. In one case, the envelope is expelled before the dense stellar cores meet. The binary survives, but its orbital separation becomes much smaller. In the other case, the envelope is not removed quickly enough, and the stars merge. A luminous red nova may accompany either severe envelope ejection or final coalescence, although the best established examples involve mergers. Those alternatives determine the future of many extraordinary systems. If a binary survives the common envelope, it can emerge as a compact pair containing a stripped stellar core and a companion. Later evolution may produce two white dwarfs, a neutron star with an ordinary star, a black hole binary, or other close combinations. Some of these systems become X-ray sources. Some may contribute to Type 1a supernova pathways. Others eventually form pairs of neutron stars or black holes close enough to merge through gravitational wave emission. Common envelope evolution is therefore one of the crucial mechanisms capable of shrinking an orbit by the enormous amount needed to create compact binaries. Let's not tell us that every common envelope ends in a merger. It allows us to study the physics deciding between survival and coalescence. How quickly is orbital energy transferred into the envelope? How much gas becomes unbound? Does recombination energy help remove it? Are jets important? How much angular momentum leaves with the outflow? These details control whether the two cores emerge as a close pair or disappear into one remnant. For many years, researchers had to estimate common envelope behavior, mainly by examining systems that had already survived it. They measured the masses and separation of a close binary, then tried to reconstruct the wider orbit that existed before the envelope formed. This is useful, but it resembles arriving after a complicated accident and determining every stage from the final positions. Red novae offer the possibility of watching part of the process while matter is still moving. The amount of ejected mass can be estimated from light curves, spectra, dust emission, and molecular observations. Expansion speeds show how much kinetic energy the gas received. The duration and shape of the bright phase indicate how long radiation remained trapped. Polarization and resolved imaging reveal whether the outflow was spherical, equatorial, or bipolar. Pre-outburst orbital measurements, when available, show how quickly the binary was losing separation. Each quantity tests a different part of common envelope theory. V1309 Scorpio demonstrated the value of continuous monitoring. Its orbital period shortened for years, the waveform changed, the system began brightening before the main eruption, and the periodic signal vanished after the merger. This sequence confirmed that a contact binary could evolve directly into a red nova. It also showed that the final outburst may have detectable warning stages rather than appearing from a completely unchanging source. V838 Monocerotis revealed another side of the process. Its multi-peaked eruption, extreme cooling, light echo, molecular remnant, and surviving wider companion showed how complicated the aftermath can become. The event indicated that mergers may occur in young multiple star systems, and that nearby companions can shape or disturb the ejector. A red nova cannot always be understood as an isolated pair in an otherwise empty environment. Other extragalactic events expand the known range of progenitors. Some arise from relatively faint systems that likely contained lower mass stars. Others come from luminous evolved stars and produce outbursts approaching the lower brightness of supernovae. This diversity suggests that non-compact stellar mergers occur across a wide span of masses and evolutionary stages. The brighter and longer-lasting events may involve more massive or more extended progenitors, although the relationship between progenitor mass and observed luminosity includes significant variation. N teaches an important lesson about astronomical transients. Similar physical processes can produce different appearances, and similar appearances can occasionally come from different processes. A massive star eruption may resemble a red nova. An incompletely observed supernova can enter the same broad luminosity range. Dust can hide a hot source and make it seem cooler. Reliable classification requires a complete sequence of evidence rather than one brightness measurement or one red spectrum. Repeated sky surveys are improving that evidence. Telescopes now image large portions of the sky every few nights, and some fields are observed even more frequently. Software compares each exposure with earlier images and flags changing sources. This makes it possible to detect a red nova during its rise instead of after its brightest stage. Archival images can then be searched for the progenitor, and follow-up telescopes can obtain spectra across visible, infrared, radio, ultraviolet, and sometimes X-ray wavelengths. Future surveys will increase the known sample dramatically. Population models have predicted that wide, sensitive time domain surveys should discover many more luminous red novae, especially in nearby galaxies. A larger sample will reveal how often mergers occur, how luminosity depends on progenitor mass, which systems produce dust most efficiently, and how many common envelope events end in coalescence instead of survival. Atta, because a single galaxy contains an enormous number of binary stars. Even if the final merger phase is brief, many systems may pass through it over the galaxy's lifetime. Most galactic red novae are probably missed because they occur behind interstellar dust, appear in crowded regions, or peak, while the relevant part of the sky is not being monitored. Infrared surveys are particularly important because mergers can surround themselves with dust before or during the outburst. The number of observed mergers also helps test stellar population models. Researchers begin with distributions of stellar masses, orbital periods, and mass ratios, then evolve millions of synthetic binaries through mass transfer and common envelope phases. The predicted red nova population depends on assumptions about processes that cannot yet be calculated perfectly. If the models produce too many bright events, too few faint ones, or the wrong durations, the assumptions must be revised. Red novae can therefore constrain the same binary physics used to predict supernovae and gravitational wave sources. A model that cannot reproduce ordinary star mergers may also be unreliable when it follows the earlier lives of future black hole or neutron star binaries. The objects are different at the final stage, but the uncertain common envelope interaction may appear in both histories. Improving one part of the calculation strengthens the rest. They also reveal that merger is not a rare exception added to an otherwise orderly theory of stars. Merging is one possible stage of normal binary evolution. A pair can remain stable for most of its life, then become unstable when one component expands. The transition may occur without either star being unusual on its own. The unusual result comes from their relationship. This changes how astronomers interpret stellar populations. A very massive-looking star may be the combined product of two less massive ones. A rapid rotator may have been spun up by accretion or merger. A star with unusual surface chemistry may contain mixed material from a former companion. A blue straggler may be older than its appearance suggests. A peculiar supergiant may be a merger remnant still losing excess heat and angular momentum. Even stellar deaths can carry this hidden history. A star that later undergoes core collapse may have gained mass through a merger. Its hydrogen envelope may be unusually thick, thin, or asymmetrical. Its core mass may not match expectations based on its current surface properties. Its rotation and magnetic field may be stronger than those of a comparable isolated star. The supernova produced at the end of that life may therefore reflect a binary interaction that occurred thousands or millions of years earlier. A merger can also influence whether a star avoids a particular death. Combining two lower mass objects does not automatically make a star massive enough to undergo core collapse. Losing large amounts of envelope material during coalescence may reduce the final mass. Mixing can extend nuclear burning and delay later stages. The result depends on the original stars and how much matter escapes. For massive binaries, the stakes are especially high, because interaction is common and stellar winds are strong. Two stars may exchange mass several times, pass through a common envelope, or merge before either forms a compact remnant. The masses of the eventual neutron stars or black holes, their spins, and their final separation all depend on that earlier history. Red novae provide a visible example of the same gravitational negotiations that remain hidden in many systems. The secret lives in the title are therefore not secret because stars deliberately conceal them. They are secret because the pair is usually too distant to resolve. The exchange of gas may be hidden by dust, and the decisive phase is short. For millions of years, a binary can look like one steady point. Only careful brightness measurements or spectra reveal that two stars are present. When unstable interaction begins, the system can surround itself with exactly the material that makes direct observation hardest. The red nova outburst briefly reverses that situation. The hidden interaction becomes brighter than the stars were before it. The light curve announces energy release. Spectral lines reveal outflows. The shift toward red records expansion and cooling. Infrared emission reveals dust. The remnant shows that the event was non-terminal. For a few months, a process usually concealed inside a common envelope becomes one of the most obvious objects in its local region of the galaxy. Then it hides again. Dust forms, the optical brightness falls, and the merged star becomes difficult to examine. This return to obscurity is not an inconvenience separate from the physics. It is part of what the event teaches. This same gas that carries away angular momentum and allows the merger to occur later absorbs the light needed to observe the result. Infrared and radio astronomy are therefore essential rather than optional additions. The chemistry of the aftermath extends the lesson beyond orbital dynamics. Molecules and dust form quickly in dense cooling gas. Some grains may survive and enter interstellar space. Red novae offer laboratories for studying dust production under conditions different from the winds of ordinary giant stars or the ejecta of supernovae. They show how a stellar interaction can create cool, chemically rich material within a short time. Their shapes teach us about angular momentum. A spherical explosion would erase much of the original orbital geometry. Red nova remnants often preserve flattened and bipolar structures, showing that the outflow was guided by rotation. The binary may have disappeared at the center, but its orbital plane remains written across the nebula. Their light curves teach us about energy transport. A rapid blue peak can reveal hot initial ejecta. A broader red maximum can trace recombination, shock interaction, or both. Plateaus show that radiation remains trapped and released gradually. Late infrared emission demonstrates that visible fading does not equal physical cooling to invisibility. Models must reproduce the full sequence, not merely the maximum brightness. The progenitors teach us about instability. A slowly rising source may already be losing mass. A shortening orbital period can warn that angular momentum is leaving. Growing infrared emission may reveal dust before the main outburst. Changes in the waveform can show that contact binary is no longer stable. These clues may eventually allow astronomers to identify another merger before its final plunge. Predicting the exact date will remain difficult. V1309. Scorpii showed a clear accelerating decline only when researchers examined the data afterward. Other contact binaries display period changes without merging. Magnetic cycles, star spots, third companions, and ordinary mass transfer can imitate parts of the signal. A reliable forecast will require several forms of evidence and a better understanding of the transition into runaway mass loss. Even without exact predictions, early identification would transform the science. Telescopes could monitor the final hundreds or thousands of orbits. Spectra could follow gas leaving through the outer Lagrange regions. Infrared instruments could watch dust appear. Radio observations could map molecular outflows. After the eruption, the same system could be followed for decades as the remnant contracted. There is a useful humility in these events. Stars are often introduced as simple spheres classified by mass, temperature, and age. That description is powerful, but a close companion can overturn it. Two ordinary stars can create an object that no isolated model would have predicted from either one alone. Their future depends not only on what they contain, but on how close they are and how they exchange motion and matter. A red nova is therefore both an ending and a beginning. It ends a binary orbit. It ends the separate evolution of two stars. Yet it begins the life of a new stellar object with a combined mass, altered composition, and complicated rotation. It creates an expanding nebula and may change whatever stellar death occurs much later. The stars do not disappear. Their identities are rearranged. Looking back across the full event, the sequence is now easier to recognize. Two stars orbit in a stable arrangement. One expands and begins filling its Roche lobe. Matter crosses toward the companion. The mass transfer becomes unstable. Gas leaves the system and carries angular momentum away. Both stars enter one common envelope. Drag shrinks the orbit. The stellar centers merge, releasing gravitational and orbital energy. The outflow expands, cools, recombines, forms molecules and produces dust. Visible light fades, while an infrared remnant continues adjusting behind the material it expelled. V838. Monocerotis showed the astonishing visible aftermath, with delayed light moving across surrounding dust. V1309. Scorpio revealed the shrinking orbit before the eruption. Together they allowed astronomers to connect the strange red light with the merger of ordinary stars. Other events in nearby galaxies now fill in the range between them, showing that mergers occur at many masses and brightness levels. And here you are, a little farther into the night than when those two stars first began circling in our story. Perhaps the room has grown quieter. Perhaps you're still listening closely. Or perhaps the details have begun drifting past without needing to be held. Either way, the red nova has given us a useful answer to the question we started with. What is a red nova, really? It is the visible disturbance produced when a close stellar relationship becomes unstable, often during the final merger of two non-compact stars. It is powered mainly by the release of orbital and gravitational energy, rather than by the surface thermonuclear runaway of a classical nova or the core destruction of a supernova. It expands and becomes red because its gas cools, recombines, forms molecules, and surrounds the survivor with dust. What remains is one unsettled star carrying the history of two. There is something reassuringly practical about that answer. We do not need to imagine a new kind of mysterious substance or an unexplained force. The ingredients are familiar: gravity, gas, heat, motion, and time. The strangeness comes from placing two stars close enough that those familiar ingredients can no longer preserve them as separate objects. If you have found this slow journey calming or interesting, you can leave a like and subscribe to Science for Sleep. It helps these quiet explorations reach other listeners who may also enjoy learning how stars merge while trying not to remain awake for the entire merger. For now, the outburst has faded. The dust continues expanding through the old orbital plane. The remnant turns behind it, gradually releasing heat and losing the excess rotation inherited from the binary. Farther away, telescopes collect the infrared light that escapes through the surrounding material. There is no longer a pair of stars completing another orbit, only one altered object and the evidence of how it formed. So settle a little more comfortably, let the remaining details loosen their grip, and remember that even an event as bright as a red nova eventually becomes quiet again. The visible light fades first, the warm dust follows more slowly, and the merged star continues its long adjustment in the dark, carrying two stellar histories forward as one.